Time didn't exist. That's not poetry, that's physics. 13.8 billion years ago, there was no before, no after, no yesterday, waiting to become today. The universe didn't explode into empty space. Space itself was born in that moment, along with matter, energy, and the dimension we call time. And every atom in your body, every photon of light that has ever reached your eyes, every star you've ever seen in the night sky, all of it traces back to a single point, smaller than the period at the end of this sentence. We know this happened. We can measure it. We can photograph it. Right now, in every direction you could possibly look, there is light travelling toward Earth that has been journeying through space for over 13 billion years. It's called the cosmic microwave background, and it is the oldest thing human beings have ever observed. A snapshot of the universe when it was only 380,000 years old, still glowing from its own birth. But here's the problem. That photograph doesn't show us the beginning, it shows us the aftermath. The moment when things had already cooled down enough for light to travel freely. Before that, there's a wall, a point past which no telescope, no matter how powerful, can ever see. And on the other side of that wall is the question that has haunted physicists, philosophers, and anyone who has ever looked up at the stars and asked the simplest, most impossible question a human being can ask. What came before? Some scientists say the question itself is meaningless. Others say the answer is stranger than anything we've imagined. This is what we actually know. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. Ahead, we will travel from the observable sky to the quantum frontier, following evidence into territory where intuition falters. And at the edge of that territory, one ancient word, nothing, will demand an entirely new reckoning from us. 13.8 billion years. That is the number. The official stamp on the cosmic birth certificate. The age of everything that has ever existed. Everywhere it has ever existed. For as long as it has ever existed. 13.8 billion trips around the sun. Except there was no sun for most of that. No Earth either. No you, no atoms in your body, no carbon, no oxygen, no elements heavier than lithium for hundreds of millions of years. Just energy and expansion, and a slow, patient construction project that eventually built galaxies and stars and rocky planets, and somehow, in at least one quiet corner of one unremarkable solar system, the kind of chemistry that looks up at the sky and asks where it all came from. The precision of that number should bother you, not because it is wrong, but because it is right to within about 1%. We are talking about the age of the universe itself, the span of time between the moment existence began and this exact second, and physicists can nail it down to 3 significant figures. 13.787 billion years, give or take 20 million. 20 million years of wiggle room sounds generous until you realise it represents an error margin smaller than the age of the oldest stars we have ever measured. Smaller than the time it took for the first galaxies to light up. Smaller, in some cases, than a single lap around the Milky Way for a star on the outer edge of the galaxy's spiral arms. How do we know this? How does anyone measure the age of the universe with that kind of confidence when the oldest human civilizations only go back a few thousand years and the oldest fossils we have ever dug up are a few billion at most? The answer comes in 2 parts, and neither one is simple. The first method looks at the oldest things we can find and counts backward. Ancient stars in globular clusters, white dwarfs cooling in the halo of the Milky Way, the chemical signatures of the first generation of suns that burned out long before our solar system even formed. Each one of those objects carries a timestamp in its light, a record of how long it has been burning or cooling or drifting. The oldest stars we have catalogued are roughly 13 billion years old. That gives us a flaw. The universe has to be at least that old, or those stars would not exist. The second method is more elegant and far more unsettling. It takes the current state of the universe, the speed at which galaxies are flying apart, the density of matter and energy filling space, the curvature of space-time itself, and runs the equations of general relativity backward like a film in reverse. Rewind far enough and everything collapses into a single point. The math tells you when that point existed, 13.8 billion years ago, The two methods agree. Different tools, different data, same answer. That is how science builds confidence. Not through one perfect measurement, but through independent lines of evidence that all point to the same uncomfortable conclusion. The universe had a beginning. It was not always here. There was a time, if you can even call it that, when none of this existed. And before that moment, the word before stops meaning anything at all. Let us be clear about what 13.8 billion years actually represents. It is not the age of matter. It is not the age of space. It is the time that has passed since a specific event cosmologists call the Hot Big Bang. The moment when the universe transitioned from an earlier state, we still do not fully understand, into the expanding, cooling, particle-filled cosmos we can observe. That transition is what the clock starts from. Anything that happened before inflation, before the Big Bang itself, lives outside the measurement. We can speculate, we can model, but we cannot see it. The observable universe begins at that moment and not a second earlier. So what has happened in those 13.8 billion years? What does the cosmic timeline actually look like when you lay it out step by step? The first thing to understand is that the universe did not explode into empty space. Space itself was created in the process. Before the Big Bang, there was no stage for the play to happen on. The Big Bang was the construction of the stage, the actors, the script, and the theatre all at once. In the first fractions of a second, the universe underwent a phase called inflation. Space expanded faster than light, stretching a region smaller than an atom into something the size of a grapefruit, in less time than it takes a photon to cross a single proton. That sounds like science fiction. It is the leading explanation for why the universe looks the way it does today. Smooth, flat, uniform on the largest scales, with just enough lumpiness to allow galaxies to form later. When inflation ended, all that energy driving the expansion had to go somewhere. It converted into matter and radiation in a process cosmologists call reheating. That is the Big Bang proper, the moment the universe filled with particles, with light, with the raw ingredients for everything that would come after. The temperature at that moment was unimaginable, trillions of degrees, hot enough that atoms could not exist, hot enough that even protons and neutrons could not hold themselves together. The universe was a seething plasma of quarks, gluons, electrons, neutrinos, photons, all of it smashing together and annihilating and reforming in a chaos so dense and so energetic that the laws of physics as we know them barely applied. About 1 second after the Big Bang, things had cooled enough for protons and neutrons to form. 1 second. That is the age of the universe when the first stable particles assembled themselves out of the quark soup. A newborn cosmos, already a second old, and in that second it had expanded from subatomic scales to something roughly the size of our solar system. The expansion was not slowing down, it was just getting started. Within the first few minutes, the universe entered a phase called nucleosynthesis. Protons and neutrons, still hot enough and close enough to fuse, began sticking together into the nuclei of light elements. Hydrogen, the simplest, one proton, stayed hydrogen. But some of those protons captured neutrons and became deuterium, heavy hydrogen. Deuterium nuclei collided and fused into helium. A tiny fraction went further and formed lithium and beryllium. Then the universe cooled past the threshold where fusion could continue, and nucleosynthesis stopped. It had lasted about 17 minutes. In those 17 minutes, the universe set the elemental composition that would define it for billions of years to come. Roughly 75% hydrogen, 25% helium, and trace amounts of lithium. Every atom of helium in your body, every helium balloon at a birthday party, every helium nucleus keeping a star's core from collapsing, was forged in those first 17 minutes. Not in stars, in the universe itself. For the next several 100,000 years, not much happened. The universe was still far too hot for atoms to form. Electrons zipped around freely, scattering photons in every direction. Light could not travel more than a short distance before slamming into another electron and bouncing away. The universe was opaque, a glowing fog with no clear lines of sight. Then, about 380,000 years after the Big Bang, the temperature dropped below a critical threshold. Electrons, which had been moving too fast to be captured, finally slowed down enough to stick to the nuclei floating around them. Hydrogen nuclei grabbed electrons and became hydrogen atoms. Helium nuclei did the same. This moment is called recombination, even though the electrons and nuclei were not recombining. They had never been together in the first place. The term stuck anyway. Once atoms formed, the universe became transparent. Photons that had been scattering off free electrons suddenly had a clear path. They streamed outward in every direction, and they have been travelling ever since. That light, stretched and redshifted by 13.4 billion years of cosmic expansion, is still reaching us today. We call it the cosmic microwave background, and it is the oldest light human beings have ever observed. It is also the earliest snapshot we have of the universe, a baby picture taken when the cosmos was less than 400,000 years old. Everything that happened before that moment is hidden behind the fog. We cannot see it directly. We can only infer it from the patterns left behind in that ancient glow. After a combination, the universe entered what astronomers call the Dark Ages. No stars yet, no galaxies, just clouds of hydrogen and helium drifting through the expanding void, slowly clumping together under the pull of gravity. This period lasted a few 100 million years, and it is one of the hardest eras to study because there was nothing bright enough to see. No light sources, no radiation, just gas falling into the gravity wells carved out by invisible clumps of dark matter. Then, somewhere between 100 and 250 million years after the Big Bang, the first stars ignited. Massive, blue, short-lived monsters that burned hydrogen at a furious rate and died in supernova explosions after only a few million years. Those explosions seeded the surrounding gas with heavier elements: carbon, oxygen, iron, silicon, the building blocks of planets, and life. From those enriched clouds, the next generation of stars formed, and galaxies began to take shape. By the time the universe was about 1 billion years old, the first galaxies had assembled. Small, irregular, clumpy things compared to the grand spirals and ellipticals we see today, but galaxies nonetheless. Over the next several billion years, those early galaxies merged, grew, cannibalized each other, and slowly built the large-scale structure we observe now. Filaments of galaxies stretching across hundreds of millions of light-years, separated by vast voids where almost nothing exists. The universe had gone from a smooth, featureless fog to a cosmic web, and it has been refining that structure ever since. Our own solar system formed about 9 billion years after the Big Bang. Roughly 4.5 billion years ago, the sun ignited, the planets coalesced from the leftover disk of gas and dust, and Earth, third rock from a middle-aged yellow star, cooled enough for liquid water to pool on its surface. A few 100 million years after that, the first life appeared. Single-celled, simple, unremarkable except for the fact that it was alive. And from that single origin, every living thing on this planet descends. Bacteria, redwoods, blue whales, fungi, humans, all of it branching from the same root, all of it made from atoms forged in the cores of dying stars billions of years before the Earth existed. That is the timeline. 13.8 billion years from a hot, dense state to a cold, vast universe filled with hundreds of billions of galaxies, each containing hundreds of billions of stars, at least 2 trillion galaxies in the observable universe alone. The observable universe, by the way, is not the whole universe. It is just the part we can see, the region from which light has had time to reach us since the Big Bang. The actual universe is almost certainly much larger, possibly infinite, but we will never know for sure because the light from those distant regions will never reach us. The expansion of space itself is carrying them away faster than their light can travel toward us. They exist, but they are beyond observation, beyond measurement, beyond proof. The observable universe is currently about 93 billion light-years across. That number is larger than 13.8 billion light-years, because space has been expanding the entire time the light was travelling. A photon that left a distant galaxy 13 billion years ago has been journeying toward us ever since, but the galaxy it left behind has been moving away the whole time. By now, that galaxy is more than 40 billion light-years away. The light arrives, but the source has receded. Multiply that across every direction, and you get a sphere of observability far larger than the age of the universe in light-years would suggest. At the moment of the Big Bang, everything we can now see, every galaxy, every star, every particle in the observable universe, was compressed into a region smaller than a centimetre across, smaller than your fingernail, smaller than a grain of sand. All of it, all the matter and energy that would eventually become 2 trillion galaxies, packed into a space so small you could hold it in your hand if your hand could survive the conditions. That is not a metaphor. That is what the math says happened. Space-time itself was created in that moment. Not the stuff inside space, but space. The fabric. The stage. There was no location for the Big Bang to happen at because locations did not exist yet. There was no surrounding void for the universe to expand into because the concept of outside had no meaning. The universe is not expanding into anything. It is expanding, period. Space is growing, distances are increasing, and everything that is not gravitationally bound is drifting farther apart. That includes us. Every galaxy beyond our local group is receding, and the rate of that recession is accelerating. Scientists attribute that acceleration to something they call dark energy, a mysterious form of energy that appears to be pushing space apart from within. We do not know what it is. We do not know where it comes from. We just know it is there because without it, the expansion should be slowing down, and it is not. The universe today is nothing like the universe a billion years ago, or 10 billion years ago, or 13 billion years ago. It has been evolving, cooling, spreading out, building complexity from simplicity. And yet the rules, the fundamental laws of physics appear to have stayed the same. The speed of light, the strength of gravity, the charge of an electron, all of it constant across billions of years and billions of light years of space. That consistency is what allows us to look backward with confidence. The universe plays fair, it follows rules, and those rules leave fingerprints we can read. The cosmic microwave background is one of those fingerprints. It is not just the oldest light we can see, it is a snapshot of the universe at a specific moment, frozen in time, carrying information about the temperature, the density, the composition, and the geometry of the early cosmos. Every telescope that has ever studied it has found the same thing. A faint glow, almost perfectly uniform, with tiny fluctuations in temperature of only a few parts per 100,000. Those fluctuations are the seeds of everything that came after. Regions that were slightly denser pulled in more matter, collapsed faster, and became the first stars and galaxies. Regions that were slightly less dense stayed empty. The pattern of those fluctuations matches the predictions of the Big Bang model so precisely that it is one of the strongest pieces of evidence we have that the story is fundamentally correct. And yet, for all the precision, for all the agreement between observation and theory, the cosmic microwave background also marks a boundary, a wall we cannot see past. Everything before that moment, before recombination, is inference. Educated inference, backed by physics and mathematics and decades of experimental verification, but inference nonetheless. We cannot see the Big Bang itself. We cannot watch inflation happen. We cannot observe the first second, the first microsecond, the first fraction of a Planck time after the universe began. All of that is hidden, locked behind the curtain of the opaque early universe. And beyond that curtain lies a question that no amount of observation can answer directly. What came before? Everything we know about the earliest moments of the universe comes from light that has been travelling toward us for over 13 billion years. That light is still arriving. Right now, at this exact second, while you're listening to these words, photons that began their journey when the universe was less than 400,000 years old are washing over this planet. They pass through walls. They pass through you. Most of them pass through everything without interacting with a single atom. We only know they're here because we built instruments sensitive enough to catch them. That light is called the cosmic microwave background, and it is the oldest thing human beings have ever observed. Not the oldest object, the oldest light. A signal so faint, so ancient, and so perfectly uniform that when it was first detected, the two men who found it thought their equipment was broken. The year was 1964. The place was Holmdel, New Jersey. Arno Penzias and Robert Wilson, two radio astronomers working at Bell Laboratories, were trying to eliminate noise from a large horn-shaped antenna that had been built for satellite communications. The antenna was sensitive, more sensitive than it needed to be for its original purpose, and Penzias and Wilson wanted to repurpose it for radio astronomy. To do that, they needed a clean baseline. They needed to point the antenna at empty sky and hear nothing. They did not hear nothing. No matter where they pointed the antenna, no matter what time of day or what season of the year, there was a persistent hiss in the background. A low-level signal at a wavelength of about 7 centimeters, right in the microwave range. It was faint, but it was everywhere. The same intensity in every direction. Day and night, summer and winter. It would not go away. Penzias and Wilson did what any good experimentalist would do. They assumed they had made a mistake. They checked the wiring. They tested the electronics. They recalibrated the receiver. The hiss remained. Then they noticed that pigeons had been nesting inside the antenna. Pigeons, as it turns out, leave behind a layer of what the scientific literature politely calls a white dielectric material. Pigeon droppings, in other words, coating the inside of a precision instrument. Penzias and Wilson cleaned out the nest, scrubbed the antenna, and chased the pigeons away. They tested again. The hiss was still there, exactly as loud as before. For over a year, they tried to identify the source. They ruled out radar. They ruled out radio interference from New York City. They ruled out the Milky Way. They ruled out the sun. Nothing they did made any difference. The signal was isotropic, the same in all directions, and it had a temperature. Not a literal temperature, but a blackbody radiation signature that corresponded to an object at about 3 degrees above absolute zero, roughly 270 degrees below freezing on the Celsius scale. That was odd. Space should be colder than that. Much colder. If the universe were truly empty, its temperature should be nearly zero. This was not zero. This was something. About 40 kilometers away, a team of physicists at Princeton University led by Robert Dicke was preparing to search for exactly this kind of signal. Dicke and his colleagues had been working through the theoretical predictions of the Big Bang model, and they realized that if the universe had started hot and dense, there should be leftover radiation from that early state still filling space today. The expansion of the universe would have stretched that radiation into longer wavelengths, cooling it down from the intense heat of the early universe into microwaves. Dicke's team was building an antenna to look for it when they heard that Penzias and Wilson had already found it by accident. The two groups connected. Penzias and Wilson had the data. Dicke's group had the explanation. In 1965, they published companion papers in the Astrophysical Journal. Penzias and Wilson reported the observation of excess antenna temperature with no identified source. Dicke and his team explained that the signal was consistent with relic radiation from a hot Big Bang. The discovery was so significant that Penzias and Wilson were awarded the Nobel Prize in Physics in 1978. They had accidentally confirmed one of the most important predictions in the history of cosmology while trying to get rid of pigeon droppings. What exactly were they detecting? To answer that, you need to understand what the universe looked like in its first few 100,000 years. Right after the Big Bang, the cosmos was a seething plasma of protons, electrons, and photons, all smashing into each other at temperatures high enough to rip atoms apart the instant they tried to form. Photons, particles of light, could not travel more than a short distance before scattering off a free electron. The universe was opaque, not dark, opaque, filled with light, but light that could not move freely. Imagine standing inside a cloud so thick you can see the glow all around you, but cannot see your own hand. That was the universe for hundreds of thousands of years. Then, about 380,000 years after the Big Bang, the temperature dropped below a critical threshold. Electrons, which had been moving too fast to be captured, slowed down enough to stick to the nuclei drifting through space. Protons grabbed electrons and became hydrogen atoms. Helium nuclei did the same. This process, confusingly named recombination even though the particles were combining for the first time, changed everything. Once atoms formed, there were no more free electrons to scatter the light. Photons that had been trapped suddenly had a clear path. They streamed outward in every direction, and the universe became transparent. That moment is called the epoch of recombination, and the light that escaped at that moment has been travelling through space ever since. It started as visible light, maybe even ultraviolet, but the expansion of the universe stretched it as it travelled. Stretch a wave and you lower its energy, shift it toward the red end of the spectrum. Stretch it for 13.4 billion years, and it ends up in the microwave range. That is what Penzias and Wilson detected. Not light from a star, not radiation from a galaxy. Light from the entire universe at once, released when the cosmos was still an infant, now cooled and redshifted into a faint microwave glow that fills every cubic centimetre of space. NASA describes the cosmic microwave background as the oldest light we can observe in the universe. That phrasing is precise. Anything that happened before recombination is hidden behind an impenetrable wall of plasma. We cannot see the first stars because there were no stars yet. We cannot see the Big Bang itself because photons could not travel freely. The cosmic microwave background is the earliest photograph we have. a snapshot taken when the universe was less than 400,000 years old, and it is the furthest back in time we will ever be able to see using light. The CMB is not just old, it is uniform. Penzias and Wilson measured the same temperature in every direction they looked. Later, more sensitive instruments confirmed that uniformity to astonishing precision. The temperature of the cosmic microwave background is almost exactly 2.725 degrees above absolute zero, and it is the same in every part of the sky to within a few parts and 100,000. That level of uniformity is a problem if you do not expect it, and it is a triumph if you do. The Big Bang model predicts a hot early universe that cools as it expands. If you run the math forward from the conditions right after the Big Bang, accounting for expansion, cooling, and the formation of atoms, you get a prediction for the temperature of the leftover radiation today. That prediction is about 3 degrees above absolute zero. Penzias and Wilson measured 2.725. The agreement is so close it borders on eerie. No other cosmological model predicted this. The steady-state theory, which was the main rival to the Big Bang in the 1960s, had no mechanism to produce a uniform microwave background. The Big Bang did. The discovery of the CMB effectively ended the debate. The universe had a beginning, and we were looking at the light from that beginning. But the CMB is not perfectly uniform. If it were, we would not be here. Perfectly uniform means no clumps, no density variations, no seeds for structure formation. A universe that's smooth would have stayed smooth forever, expanding into a cold, featureless void with no stars, no galaxies, no planets, no us. The fact that we exist means there had to be imperfections, tiny fluctuations in density that gravity could latch onto and amplify over billions of years. Those fluctuations are there, they're just incredibly small. In 1992, NASA's Cosmic Background Explorer satellite known as COBE detected them for the first time. Temperature variations in the CMB of about 1 part in 100,000. Regions that were slightly hotter and regions that were slightly cooler, scattered across the sky in a pattern that looked random but was not. Those tiny differences in temperature corresponded to tiny differences in density in the early universe. The hotter spots were regions where matter was slightly less dense, where photons had an easier time escaping. The cooler spots were regions where matter was slightly more dense, where gravity was already starting to pull things together. Over the next few 100 million years, those denser regions collapsed under their own gravity, pulling in more matter, forming the first stars, the first galaxies, and eventually the large-scale structure we see today. The fluctuations in the cosmic microwave background are the seeds of everything. Every galaxy, every star, every planet, every atom in your body traces back to a quantum fluctuation in the first fractions of a second after the Big Bang that left its fingerprint in the CMB. The pattern of those fluctuations is not random. It is a specific distribution predicted by the physics of the early universe. The sizes of the hot and cold spots, the way they are distributed across the sky, the statistical properties of their clustering, all of it matches the predictions of the Big Bang model with inflationary expansion. Inflation is the idea that the universe underwent a brief period of exponential expansion in the first fraction of a second, stretching quantum fluctuations up to cosmic scales. Those fluctuations froze into the fabric of space, and when the universe became transparent 380,000 years later, they showed up as temperature variations in the CMB. Measuring those variations required better instruments than COBE. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe to UMAP, which mapped the CMB in far greater detail. WMAP's data allowed cosmologists to measure the age of the universe, the density of matter and dark matter, the amount of dark energy, and the rate of expansion with unprecedented precision. The age came out to 13.77 billion years, within about 1% of the current best estimate. The density of ordinary matter, the stuff that makes up atoms, came out to about 5% of the total energy density of the universe. Dark matter accounts for about 27%. Dark energy, the mysterious force driving the accelerated expansion, makes up the remaining 68%. In 2009, the European Space Agency launched the Planck satellite, which pushed the measurements even further. Planck mapped the CMB at multiple frequencies, with a resolution sharp enough to see fluctuations smaller than 1/10 of a degree across the sky. The data confirmed everything WMAP had found and tightened the error bars even more. current best estimate for the age of the universe from Planck is 13.787 billion years. The temperature of the CMB is 2.7255 degrees Kelvin. The geometry of the universe is flat to within measurement error. Every number fits, every prediction matches. The cosmic microwave background is not just evidence for the Big Bang, it is a detailed record of the conditions in the early universe, encoded in the pattern of temperature fluctuations across the sky. By analysing that pattern, cosmologists can test models of inflation, measure the curvature of space, constrain the properties of dark matter, and probe the physics of the first few 100,000 years after the universe began. The CMB is the single most important dataset in observational cosmology. Without it, we would still be guessing. It is worth pausing on what it means that this light has been travelling for over 13 billion years and only now reached us. The photons in the cosmic microwave background were emitted from every point in space when the universe was 380,000 years old. Since then, space has been expanding. The regions that emitted those photons have receded, carried away by the expansion. The light left behind has been stretched and redshifted, but it kept travelling. And because the universe was everywhere, the CMB comes from everywhere. It is not a point source, it is a shell. The surface of last scattering, the moment when the universe became transparent, forms a sphere around us, and we are at the centre of that sphere not because we are special, but because every observer in the universe sees the same thing. Every galaxy, every star, every point in space has its own cosmic microwave background coming from the regions that are now 46 billion light-years away in every direction. That distance, 46 billion light-years, is the radius of the observable universe. It is larger than 13.8 billion light-years because space itself has been expanding while the light was travelling. The photons we detect today left regions that were much closer when they were emitted, but those regions have since been carried away by expansion. The CMB maps the edge of what we can ever hope to see. Beyond that shell lies more universe, but the light from those regions has not had time to reach us yet, and because the expansion is accelerating, it may never reach us. The cosmic microwave background is both a window into the past and a boundary on observation. The discovery of the CMB did more than confirm the Big Bang. It ruled out alternatives. The steady-state theory, championed by astronomers like Fred Hoyle, proposed that the universe had no beginning. New matter was continuously created as space expanded, keeping the density constant over time. The theory was elegant and it avoided the uncomfortable question of what came before, but it made no prediction for a relic radiation bath filling the universe. When Penzias and Wilson found the CMB, the steady-state model had no explanation. The Big Bang did. Within a few years, the steady-state theory was abandoned by most of the scientific community. The evidence was too strong. There were other competing ideas as well, models involving oscillating universes or collapsing and re-expanding cosmologies. None of them predicted the specific properties of the CMB. The temperature, the uniformity, the tiny fluctuations, all of it pointed back to a hot, dense beginning, followed by expansion and cooling. The cosmic microwave background was not just consistent with the Big Bang, it was a prediction of the Big Bang, made decades before it was observed, and the match between theory and observation was exact. Popular descriptions often call the CMB the heat left over from the Big Bang. That phrasing is more than a metaphor. It is literally true. The early universe was hot, millions of degrees, and as it expanded, it cooled. The photons that filled space at that time have been cooling ever since, their energy diluted by the stretching of space. What started as visible or ultraviolet light has been redshifted into microwaves. The temperature of that radiation, 2.7 degrees above absolute zero, is exactly what you would expect from a universe that started hot and has been expanding for 13.8 billion years. The math works, the observations match, the picture fits together. And yet, for all its power as evidence, the cosmic microwave background also marks a limit. It is a wall. Everything before recombination is hidden. The first 380,000 years of the universe are invisible to direct observation, because photons could not travel freely during that time. We can infer what happened from the CMB's pattern, from the physics of nucleosynthesis, from the distribution of elements and the properties of dark matter, but we cannot see it. The earliest light we can observe is the CMB itself, and anything before that is inference theory and mathematics. The temperature fluctuations in the CMB tell us that the universe was not born perfectly smooth. There were quantum fluctuations, tiny random variations in density, present from the very beginning. Inflation stretched those fluctuations to cosmic scales, and they became the seeds of galaxies. Gravity took over from there, pulling matter into clumps, forming stars, igniting fusion, building the elements heavier than hydrogen and helium. The story from recombination to today is one of increasing complexity. Structure forming from simplicity, atoms clumping into stars, stars clumping into galaxies, galaxies clustering into superclusters, all of it driven by gravity acting on the initial conditions set by the Big Bang. The cosmic microwave background is the most direct evidence we have that the universe had a beginning. It is not a theoretical construct. It is not a model-dependent inference. It is light. Real photons detectable with real instruments, carrying information from a time when the universe was less than 400,000 years old. Every prediction the Big Bang model makes about the CMB has been confirmed. The temperature, the spectrum, the uniformity, the fluctuations, the polarization patterns, all of it matches. No other theory comes close, and yet the CMB raises as many questions as it answers. Why was the early universe so uniform? Why were the fluctuations so small? What set the initial conditions that led to the specific pattern we observe? The answers to those questions point backward, past recombination, past the first 380,000 years, all the way back to the first moments after the Big Bang. The CMB is a photograph, but it is not the whole story. It is a snapshot of the universe at one specific moment in time, and to understand what came before, we need to go deeper. We need to look at what the Big Bang itself actually was. The universe did not explode. That needs to be said clearly and upfront, because almost every popular description of the Big Bang gets this wrong. The name itself is misleading. Big Bang sounds like a detonation. It conjures images of a bomb going off in the void, matter and energy flying outward into empty space like shrapnel from a grenade. That is not what happened. There was no bomb. There was no void to explode into. There was no empty space waiting to be filled. The Big Bang was not an explosion in space. It was the expansion of space itself. Space, the fabric that we move through, the three-dimensional stage on which every event in your life has played out, did not exist before the Big Bang. Time, the forward march of cause and effect, the sequence that separates yesterday from tomorrow, did not exist either. The Big Bang was the moment when both came into being, not a detonation inside an existing container, but the creation of the container itself. Everything that would eventually become the observable universe, every galaxy, every star, every atom, was not scattered across a vast region at the moment of the Big Bang. It was all in the same place. Not because it was packed tightly together inside a small volume of space, but because space itself had not yet stretched out. The distances we measure today, the light years separating stars and galaxies, did not exist yet. They were created by expansion, not by objects moving apart through a pre-existing void. NASA is careful about this. They describe the Big Bang as the moment the universe began expanding from an extremely hot, dense state. Not an explosion. An expansion. The difference matters because it changes what questions you can ask. If the Big Bang were an explosion, you could ask what it exploded into. If it is an expansion of space, that question has no meaning. There is no outside. There is no surrounding emptiness. Space itself is what is growing, and asking what lies beyond space is like asking what is north of the North Pole. The question assumes a framework that does not apply. The earliest state we can describe, the starting point for every timeline you will ever see, is called a singularity. That word shows up constantly in cosmology papers, in documentaries, in textbooks. It is also one of the most misunderstood terms in physics. A singularity in mathematical terms is a point where the equations break down, where the numbers go to infinity, where the models stop giving useful answers. The singularity at the beginning of the universe is not an object anyone has seen or measured. It is a signpost marking the edge of our ability to calculate what happened. Popular summaries describe the singularity as an infinitely dense point, infinitely hot, containing all the matter and energy that would become the universe. That description is technically correct if you run general relativity backward in time all the way to zero. But physicists are not comfortable with infinities. Infinities usually mean you are missing something. They are red flags indicating that your theory has reached its limits. General relativity works beautifully for describing planets, stars, black holes, galaxies, the large-scale structure of the cosmos. It works less well when you try to apply it to regions smaller than the Planck length, about 10 to the power of negative 35 meters, or to timescales shorter than the Planck time, about 10 to the power of negative 43 seconds. At those scales, quantum mechanics takes over, and quantum mechanics does not play nicely with general relativity. The two theories describe the universe in incompatible ways, and no one has yet figured out how to unify them. The singularity, then, is not a fact. It is a placeholder, a label for the region where our current physics stops working, and something else, some deeper theory we have not discovered yet, would need to take over. Cosmologists talk about the singularity because it is the natural conclusion you reach if you follow general relativity all the way back. But most of them will tell you, if you ask directly, that the universe probably did not actually start as a point of infinite density. Something else happened at those extreme conditions. We just do not know what. What we do know is that the universe was once unimaginably small, unimaginably hot, and unimaginably dense. Not infinite, but close enough that the difference does not matter for most practical purposes. The entire observable universe, everything we can see today out to a radius of 46 billion light-years, was compressed into a region smaller than a centimetre across. Some estimates put it smaller than a proton. All the matter, all the energy, all the space that would eventually contain 2 trillion galaxies, packed into a volume you could hold between your thumb and forefinger. At that scale, temperature loses its ordinary meaning. Temperature, in the everyday sense, is a measure of how fast particles are moving. Hotter means faster. But in the first moments after the Big Bang, particles as we know them did not exist yet. The 4 fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were not yet distinct. They were unified into a single force, operating under rules we can only guess at. This is the Planck epoch, lasting from time 0 to about 10 to the power of negative 43 seconds. A span of time so short that light, the fastest thing in the universe, could only travel a distance of 10 to the power of negative 35 meters, smaller than any particle we have ever detected. Smaller than the wavelength of any radiation we could ever hope to observe. During the Planck epoch, space-time itself was quantum, not smooth, not continuous, but foamy, fluctuating, flickering in and out of existence at scales where the concepts of distance and duration start to blur. Physicists call this quantum foam. It is not something you can see or touch or measure directly. It's a consequence of trying to apply quantum mechanics to space-time. And it suggests that at the smallest scales the universe is not a fixed stage but a seething sea of uncertainty. The Planck epoch is a theoretical blind spot. We have no experiments that can probe those conditions. We have no observations that can reach back that far. What we have are equations, and those equations tell us that the universe at that moment was governed by physics we do not yet understand. The Planck epoch ended when the universe cooled enough and expanded enough for gravity to separate from the other forces. That happened around 10 to the power of negative 43 seconds. Gravity, the weakest of the 4 forces by far, peeled off first and began behaving the way it does today. The other 3 forces, electromagnetism, the strong force and the weak force, remained unified for a bit longer, bound together in what physicists call the grand unified force. This phase lasted until about 10 to the power of negative 37 seconds, when the strong force split off. That moment, the breaking of the grand unified force, may have triggered cosmic inflation. Inflation is one of the strangest, most important ideas in modern cosmology. The theory was proposed in the early 1980s by physicist Alan Guth, and it solves several problems that the standard Big Bang model could not explain on its own. The core idea is that the universe underwent a brief period of exponential expansion in the first fraction of a second, growing faster than the speed of light. Not faster than light through space, which is impossible, but faster than light because space itself was expanding. Objects embedded in space cannot move through space faster than light, but space itself has no speed limit. It can stretch as fast as it wants. NASA describes this expansion as occurring faster than the speed of light for a fraction of a second. That phrasing undersells what happened. During inflation, the universe did not just grow quickly, It doubled in size over and over again in rapid succession. Every tiny fraction of a second, the universe doubled, then doubled again, then again. The numbers are staggering. Estimates from the Harvard Center for Astrophysics suggest the universe grew by a factor of 10 to the power of 26 in a span of time shorter than the blink of an eye. A region smaller than an atom became larger than a galaxy in less than a trillionth of a second. Inflation explains why the universe looks so uniform. Before inflation, the universe was small enough that different regions could interact, exchanging energy and reaching thermal equilibrium. Then inflation kicked in and stretched everything apart so fast that regions which had been in contact were suddenly separated by vast distances. They kept the same temperature because they started in equilibrium, and inflation froze that uniformity in place. Without inflation, there is no good explanation for why the cosmic microwave background has the same temperature in all directions to within a few parts in 100,000. With inflation, it is exactly what you would expect. Inflation also explains the flatness of the universe. Space can be curved. General relativity allows for three possibilities: positive curvature, like the surface of a sphere, where parallel lines eventually converge; negative curvature, like the surface of a saddle, where parallel lines diverge; and flat, where parallel lines stay parallel forever. Observations of the cosmic microwave background tell us the universe is flat, or very close to it, to within measurement error. That flatness is unstable. If the universe started out even slightly curved, expansion should have amplified that curvature over time. A universe that was almost flat should have become obviously curved by now. The fact that it is still flat after 13.8 billion years is a problem unless something flattened it early on. Inflation does exactly that. Stretch any surface enough and it looks flat. Inflate a balloon to the size of the Earth and the surface looks flat to anyone standing on it. Inflate the universe by a factor of 10 to the power of 26, and any curvature it started with gets smoothed out completely. When inflation ended, all the energy driving the expansion had to go somewhere. It converted into particles: quarks, electrons, photons, neutrinos. All the fundamental building blocks of matter and light came into existence in that moment. This is called reheating, and it marks the transition from the inflationary epoch to the hot Big Bang proper. The universe went from cold and empty, with all its energy locked up in the inflation field driving the expansion, to hot and dense, filled with a seething soup of particles colliding and annihilating and reforming at temperatures high enough to make the core of a star look frigid by comparison. At this point, the universe was about 10 to the power of negative 35 seconds old, still unimaginably young. The temperature was around 10 to the power of 27 degrees. That number is so large it does not map onto any human experience. The core of the Sun sits at about 15 million degrees. The hottest thing ever created in a laboratory, inside the Large Hadron Collider, reached about 5 trillion degrees for a fraction of a second. The early universe was 1 trillion times hotter than that. At those temperatures, particles do not just move fast. They collide with enough energy to create new particles out of pure kinetic energy. Matter and antimatter pairs popped into existence, annihilated each other back into photons, and the photons collided to create more matter-antimatter pairs. The universe was a cauldron. The particles at this stage were not atoms. They were not even protons or neutrons. Those composite particles made of quarks bound together by the strong force could not exist yet. The universe was too hot. Anytime quarks tried to stick together, thermal energy ripped them apart. This phase is called the quark epoch. The universe was a plasma of free quarks, gluons, electrons, neutrinos, and photons, all interacting furiously. The quark epoch lasted until the universe was about 10 to the power of negative 12 seconds old, roughly 1 trillionth of a second. At that point, the temperature had dropped to about 10 trillion degrees, still absurdly hot by any ordinary measure, but cool enough for quarks to bind together into protons and neutrons without immediately being torn apart. The moment when quarks combined into protons and neutrons is called the hadron epoch. Hadrons are composite particles made of quarks, and they include protons, neutrons, and a zoo of short-lived particles that decay almost immediately. For the first time, the universe contained particles that would survive long enough to become part of atoms. Protons, the nuclei of hydrogen, the simplest and most common element in the universe, began accumulating. Neutrons, slightly heavier than protons and unstable when left alone, started forming as well. Free neutrons decay into protons with a half-life of about 10 minutes, but if they can find a proton to bind to quickly enough, they stabilize. That binding would become important later during nucleosynthesis, but for now, the universe was still too hot for any kind of stable nuclei to form. By the time the universe was about 1 second old, the temperature had dropped to around 10 billion degrees. NASA describes this as an extremely hot primordial soup of light and particles. Protons and neutrons were stable. Electrons and neutrinos were zipping around freely. Photons were scattering off everything. The universe was still opaque, still a chaotic mess, but it was beginning to settle into something recognizable. The forces of nature were behaving the way they do today. The particles were the same ones we can create and study in accelerators. The physics was well understood. From 1 second onward, cosmologists can describe the evolution of the universe with a high degree of confidence. Everything before that first second is more speculative, relying on theories that have not been tested at the relevant energy scales. Between 1 second and a few minutes, the universe cooled enough for nucleosynthesis to begin. Protons and neutrons collided and stuck together, forming the nuclei of light elements. Deuterium first, heavy hydrogen with 1 proton and 1 neutron, then helium with 2 protons and 2 neutrons. Tiny amounts of lithium and beryllium also formed. This process lasted about 17 minutes, and by the end of it, the universe had settled into a composition of roughly 75% hydrogen and 25% helium by mass. That ratio has barely changed in 13.8 billion years. Stars have fused some of that hydrogen into heavier elements, but the overall balance between hydrogen and helium set during nucleosynthesis remains the same today. Every helium atom you have ever encountered, whether in a balloon or a star or the sun, was forged in the first 17 minutes after the Big Bang. After nucleosynthesis, the universe entered a long, quiet period. It was still too hot for atoms to form. Electrons were moving too fast to be captured by nuclei. The universe was a plasma, ionized, opaque, filled with light that could not travel more than a short distance before scattering. This phase lasted for hundreds of thousands of years. Nothing dramatic happened during that time. The universe just expanded and cooled. The temperature dropped from billions of degrees to millions of degrees to hundreds of thousands of degrees. Slowly, steadily, the energy drained away, carried off by the expansion of space itself. Then, about 380,000 years after the Big Bang, the temperature dropped below a critical threshold. Electrons slowed down enough to be captured by protons and helium nuclei. Atoms formed. The universe became transparent. The cosmic microwave background was released, and the universe went from opaque to clear in what was, by cosmic standards, an instant. That transition marked the end of the early universe and the beginning of the era we can observe directly. Everything that happened before recombination, the entire sequence from the Planck epoch through inflation, reheating, the quark epoch, nucleosynthesis, and the long cooling period, is reconstructed from theory, from particle physics experiments, and from the fingerprints left behind in the cosmic microwave background. We cannot see it directly, we can only infer it, and yet the picture that emerges is remarkably consistent. The predictions made by Big Bang nucleosynthesis about the abundance of hydrogen, helium, and lithium match the observations. The predictions made by inflation about the uniformity and flatness of the universe match the measurements. The timeline reconstructed from particle physics experiments matches the conditions inferred from the CMB. The Big Bang was not an explosion, it was an expansion, not a detonation of matter and energy into pre-existing space, but the creation of space itself, carrying matter and energy along for the ride. The singularity at the beginning is not a confirmed fact, but a mathematical artifact marking the limits of our current theories. The universe was once unimaginably small, hot, and dense, but whether it was ever truly a point of infinite density is a question that current physics cannot answer. What we do know is that the universe began in a state far outside the range of everyday experience, governed by forces and particles we can barely describe, and that within the first second, it had cooled enough for the physics we understand to take over. The early universe was violent, chaotic, extreme in every measurable way, and yet it was also precise. The balance between matter and antimatter had to be just right, or everything would have annihilated, and the universe would be empty. The rate of expansion had to be just right, or the universe would have collapsed back on itself or flown apart so fast that no structures could ever form. The strength of the forces, the masses of the particles, the energy density of space, all of it had to fall within a narrow range for the universe to become anything other than a featureless void. It did, and now, 13.8 billion years later, we are here, looking back, trying to understand how something came from what appears to have been nothing. Nothing does not exist. That sentence should bother you. It is either obviously true or completely nonsensical depending on how you read it, and the ambiguity is not an accident. It is the entire problem. When we talk about what existed before the Big Bang, we're asking what was there before space, before time, before matter, before energy. The instinct is to answer nothing. Empty void. Absence. The philosophical concept of non-existence. But physics does not allow that answer. Not because physicists are being difficult, but because the universe, at its most fundamental level, refuses to sit still. Even when you remove everything, something remains. And that something changes everything. Start with the intuitive version of nothing, the one most people carry around in their heads. Close your eyes and imagine a box. Now remove everything inside it. Take out the air, the dust, the stray photons bouncing around. Pull out the atoms, the molecules, every last particle. What are you left with? Empty space. A perfect vacuum. Nothing. That feels like a reasonable answer. It matches how we use the word in everyday language. An empty room, an empty wallet, an empty tank. Nothing inside. The container remains, but the contents are gone. Philosophy has spent thousands of years wrestling with this idea. Ancient Greek philosophers debated whether a true void could exist. Aristotle argued that nature abhors a vacuum, that empty space was impossible because something would always rush in to fill it. Later thinkers disagreed. Descartes believed space itself was a substance, an invisible medium filling the gaps between objects. Newton thought space was absolute, a fixed stage on which objects moved, existing independently of the matter within it. Leibniz countered that space was relational, defined only by the positions and distances between objects, meaningless without something to measure. The arguments went in circles for centuries because they were arguments about definitions, not observations. There was no way to test who was right. No experiment that could isolate a patch of true emptiness and measure what, if anything, it contained. Then quantum mechanics arrived in the early 20th century and made the entire debate obsolete. Physics replaced philosophy not by answering the old questions, but by showing that the questions themselves were based on faulty assumptions about how reality works at small scales. Quantum field theory, the framework that describes particles and forces at the most fundamental level, treats the vacuum differently than classical physics ever did. In this picture, space is not an empty container waiting to be filled. It is not a passive stage where particles happen to exist. Space is itself a thing, a dynamic, fluctuating, energy-filled thing. Even when you remove every particle, every atom, every photon, you are left with something physicists call the quantum vacuum. And the quantum vacuum is not empty, it is busy. Here is how it works. Every type of particle, electrons, quarks, photons, neutrinos, corresponds to a field that fills all of space. These are not metaphorical fields. They are physical entities, mathematical structures that have values at every point in the universe. An electron is not a tiny ball bouncing through empty space. It is a localized excitation in the electron field, a ripple, a wave, a disturbance in something that was already there. The field is the fundamental thing. The particle is just what happens when the field gets excited. These fields never turn off. Even in the absence of particles, the fields remain, and they are not Jing-Ji. Quantum mechanics, specifically the Heisenberg uncertainty principle, forbids any system from being perfectly still. There is always some residual motion, some minimal amount of energy that cannot be removed. This is called zero-point energy, and it is not optional. It is a direct consequence of the mathematical structure of quantum mechanics. You cannot have a field with exactly zero energy and exactly zero fluctuation at the same time. The uncertainty principle says that if you try to pin down the energy precisely, the fluctuations grow. If you try to eliminate the fluctuations, the energy becomes uncertain. you're stuck with both. What does that mean in practice? It means that even in the emptiest possible region of space, with no particles, no radiation, no matter of any kind, the quantum fields are vibrating, oscillating, humming at the lowest possible energy state, which is still greater than zero. The vacuum is not a featureless void. It is a seething ocean of quantum activity happening at scales far too small and far too fast for us to observe directly. Physicists call this the zero-point field, and its effects are real, measurable. We have detected them in laboratories. One of the cleanest demonstrations is called the Casimir effect, first predicted by Dutch physicist Hendrik Casimir in 1948. Take two flat, uncharged metal plates and place them very close together in a vacuum, just a few micrometers apart. Classical physics says nothing should happen. There are no particles pushing on the plates, no air pressure, no electric charge. The plates should just sit there, inert. They do not. The plates are pushed together by a tiny but measurable force. The explanation comes from quantum field theory. The vacuum between the plates and the vacuum outside the plates are not the same. Outside, all possible wavelengths of virtual photons can fluctuate in and out of existence. Between the plates, only wavelengths that fit between the boundaries can exist. Longer wavelengths are excluded. That creates an imbalance. There is more quantum vacuum energy pushing on the outside of the plates than on the inside, and the net result is a force pulling them together. The Casimir effect was measured experimentally in 1997 by Steve Lamoureux at the University of Washington. The agreement between theory and measurement was precise. The force is tiny, only noticeable at very small distances, but it is there. The vacuum has structure, it pushes back, and the energy responsible for that push comes from quantum fluctuations that exist even when there are no real particles present. Virtual particles are another consequence of the same physics. In the quantum vacuum, particle-antiparticle pairs can spontaneously pop into existence, exist for a brief moment, and then annihilate back into the vacuum. An electron and a positron appear out of nothing, live for a time so short it makes a nanosecond look like an eternity, and then collide and vanish. These are not real particles in the sense that you can catch one and put it in a detector. They exist only as temporary fluctuations allowed by the uncertainty principle. Energy is not conserved during their brief existence, but that is okay as long as they disappear quickly enough. The shorter the time they exist, the larger the energy violation they can get away with. Heisenberg's uncertainty principle sets the limits, and as long as the particles respect those limits, quantum mechanics permits them. These virtual particles are not speculation. They have measurable effects. They contribute to the mass of real particles, altering the properties of electrons and quarks in ways that have been confirmed to extraordinary precision. They affect the behavior of light passing through strong magnetic fields. They play a role in the decay rates of certain particles. The quantum vacuum is not a passive backdrop. It is an active participant in every process that happens at the subatomic level. Now take that picture, the vacuum filled with fields, with zero-point energy, with virtual particles flickering in and out of existence, and ask what happens at the smallest possible scales. At distances comparable to the Planck length, about 10 to the power of negative 35 meters, and timescales comparable to the Planck time, about 10 to the power of negative 43 seconds. These are not arbitrary limits. They are the scales at which quantum mechanics and general relativity both become important, and those two theories do not agree on how to describe what happens. General relativity treats space-time as smooth, continuous, a gently curving fabric that bends in response to mass and energy. Quantum mechanics treats everything as probabilistic, grainy, fundamentally uncertain. When you try to describe space-time itself using quantum mechanics, you get a picture that is anything but smooth. At the Planck scale, space-time is thought to fluctuate wildly. Distances and durations become uncertain. The geometry of space itself becomes probabilistic. The neat, orderly grid of coordinates you use to describe where and when something happens dissolves into what physicists call quantum foam. Quantum foam is not something we can observe directly. No telescope, no particle accelerator, no instrument we have or are likely to build anytime soon can probe scales that small, but the mathematics of quantum field theory, when applied to gravity, suggests it must be there. Just as the electromagnetic field has zero-point energy and virtual particles, space-time itself, treated as a quantum field, should have fluctuations. At large scales, those fluctuations average out and space-time looks smooth. At the Planck scale, the fluctuations dominate. Space and time themselves become uncertain, flickering, foaming at the edges of measurability. The term quantum foam was coined by physicist John Wheeler in the 1950s. He described it as a turbulent sea of space and time, constantly churning at the smallest scales, with wormholes and tiny black holes popping in and out of existence, topology shifting and changing in ways that make no sense in the smooth space-time of general relativity. Whether Wheeler's specific picture is correct is still an open question. We do not have a complete theory of quantum gravity yet, but the general idea that space-time cannot be perfectly smooth at the Planck scale is widely accepted. Something has to give when you try to combine quantum mechanics with general relativity, and quantum foam is one of the leading candidates for what that something looks like. So when we talk about nothing, when we try to imagine what might have existed before the Big Bang, we're not talking about a serene, empty void. We're talking about a quantum vacuum filled with fields, humming with zero-point energy, fluctuating with virtual particles, and at the deepest level, foaming with space-time itself, writhing and shifting in ways that blur the distinction between here and there, between now and then. That is the scientific version of nothing, and it is anything but empty. This creates a profound shift in how we think about the origin of the universe. The classical picture, the one that dominated philosophy and religion for most of human history, assumed that something cannot come from nothing, that there must be a first cause, a prime mover, something or someone that set the whole process in motion. The logic seemed airtight. If there was once nothing, and now there is something, the transition requires an external agent, a creator, a cause outside the system. But quantum mechanics offers a different possibility. If nothing, defined scientifically, is not actually empty, then the transition from nothing to something is not the impossible leap it appears to be. Physicist Lawrence Krauss makes this argument explicitly in his book, A Universe from Nothing. He points out that the quantum vacuum, with its inherent energy and fluctuations, provides a mechanism for universes to begin without any external input. A quantum fluctuation, amplified by something like cosmic inflation, could grow into an entire universe. The energy needed to create all the matter and radiation in the cosmos could come from the gravitational field, which in a certain sense carries negative energy. Add up the positive energy of matter and radiation and the negative energy of gravity, and the total might be zero. A universe from nothing, not because something magical happened, but because the bookkeeping works out. The total energy balance is zero, and quantum mechanics permits fluctuations that temporarily violate energy conservation, as long as they settle back into balance over time. Not everyone agrees with Krauss's framing. Some philosophers and physicists argue that the quantum vacuum, with its fields and zero-point energy, is not nothing in the philosophical sense. It is something, a something with properties, with laws, with structure. If you start with a quantum vacuum, you are not starting with absolute non-existence. You are starting with a framework, a set of rules, a substrate that already exists. The question then becomes, where did that substrate come from? What explains the existence of quantum fields, the laws of quantum mechanics, the framework within which fluctuations can occur? Krauss's answer pushes the mystery back a step, but it does not eliminate it. Philosopher and theologian William Lane Craig has been one of the most vocal critics of this approach. He argues that calling the quantum vacuum nothing is a bait and switch. The quantum vacuum, he points out, is not nothing. It is a complex, structured, energy-filled state governed by the laws of physics. If those laws exist, if that state has properties, then it is something, and the question of why there is something rather than nothing remains unanswered. Craig's critique is philosophically sharp, and it highlights the gap between the scientific definition of nothing and the philosophical one. The debate hinges on definitions. If nothing means the absence of matter, the absence of particles, the absence of anything you could point to and call a thing, then the quantum vacuum qualifies. It is empty in that sense. But if nothing means the absence of everything, including fields, laws, structure, potential, then the quantum vacuum does not qualify. It is emphatically not nothing. It is the lowest energy state of a system that already has rules, and those rules, the laws of quantum mechanics, the structure of quantum fields, are themselves something that needs explaining. Physics does not have an answer to the question of why the laws of physics exist. Why quantum mechanics instead of some other framework? Why these fields, these particles, these forces? The laws themselves are taken as given, as the starting point for calculation and prediction. You can ask how the laws work, what they predict, how they relate to one another. You cannot, within the framework of physics, ask why they exist in the first place. That question lies outside the domain of science. It is metaphysics, philosophy, theology, depending on your preference. Science can tell you what happens given certain laws. It cannot tell you why those laws hold rather than others, or why there are laws at all. And yet the quantum vacuum, empty as it is of particles, gives us a picture of what nothing looks like when filtered through the rules of quantum mechanics. It is not static. It is not calm. It is not peaceful. It is violent, chaotic, constantly fluctuating at scales too small to see. If the universe began from something like a quantum fluctuation, if the Big Bang was the moment when a tiny ripple in the quantum foam got amplified into an expanding cosmos, then the origin of everything we see might not require a cause in the traditional sense. It might just require the laws of quantum mechanics, the existence of fields, and enough time, or rather enough quantum uncertainty, for a fluctuation to occur. The implications are unsettling. If the universe can begin as a quantum fluctuation, then the boundary between something and nothing becomes blurry. Existence stops being a binary state and starts looking more like a probabilistic outcome. The universe is not an object that was created at a single moment by a deliberate act. It is a process, an event, a fluctuation in a deeper substrate that may have always existed in some sense. The Big Bang is not the beginning of everything. It is the beginning of this universe, this particular configuration of space and matter and energy. The substrate, the quantum fields, the laws that govern them, those might be eternal, existing outside of time, not created but simply there as the background against which events like the Big Bang can occur. This picture is strange. It violates our intuitions about causality, about creation, about the nature of existence itself, but it is consistent with what we know about quantum mechanics, and it provides a framework for thinking about the origin of the universe without invoking anything outside the system. No external creator, no first cause, just the quantum vacuum, humming along, occasionally fluctuating into something large and structured enough to call a universe. Whether that is the correct picture is still an open question. We do not have a complete theory of quantum gravity. We cannot observe the Planck scale directly. We cannot test whether quantum fluctuations can actually produce universes. The idea is speculative, built on extrapolations of known physics into regimes where we have no experimental data. But it is not wild speculation. It is grounded in the best theories we have, and it makes predictions that are in principle testable. If cosmic inflation happened, and the evidence strongly suggests it did, then the seeds of galaxies and large-scale structure should have originated as quantum fluctuations during the inflationary epoch. Those fluctuations left their fingerprints in the cosmic microwave background, and we have measured them. The match between theory and observation is precise. Quantum fluctuations, amplified by inflation, became the structure of the universe. That much we know. The harder question is whether the universe itself began the same way. Whether the Big Bang was just a larger version of the same process, a quantum fluctuation in a pre-existing vacuum that got amplified into an entire cosmos. If so, then the question of what existed before the Big Bang has a surprising answer. Not nothing. Not in the philosophical sense, but not something in the ordinary sense either. A quantum vacuum. A state of minimal energy, maximal uncertainty, filled with fields that fluctuate, that foam, that occasionally, given enough time or enough quantum weirdness, give birth to universes. And if that is the case, then the question shifts. It is no longer what came before the Big Bang. It is what is the nature of the quantum vacuum itself, and why does it have the properties it has? Why these fields and not others? Why these laws and not different ones? Why is there a quantum vacuum at all, rather than the true philosophical nothing that contains no fields, no laws, no potential for anything to happen? Those questions remain unanswered. They may remain unanswered forever. But the progress we have made is significant. We have gone from asking how something can come from nothing, to asking why the quantum vacuum has the specific properties that allow universes like ours to emerge. That is a narrower question, a more precise question, and it is one that physics, in principle, might eventually be able to answer. The quantum vacuum is not nothing, but it is as close to nothing as the universe allows, and the fact that it is not truly empty, that it writhes with energy and fluctuations even in the absence of particles, tells us that our intuitive understanding of emptiness is wrong. Nothing, in the way we imagine it, does not exist. It cannot exist. The laws of quantum mechanics forbid it. Space itself, even stripped of every particle, every photon, every atom, is still something, and that something has consequences. It has energy, it has structure, it has the capacity to fluctuate, to change, to create. The vacuum is not a passive void, it is the stage, the actor, and the script all at once. And if the universe began from a fluctuation in that vacuum, then the story of creation is not a story of something coming from nothing. It is a story of structure emerging from chaos, of order crystallizing out of quantum uncertainty, of a universe unfolding from the inherent restlessness of reality itself. That restlessness brings us to the next uncomfortable truth. If the quantum vacuum exists, if it has properties and laws and the capacity to fluctuate into universes, then we still have not answered the deepest question. We have only rephrased it. The question is no longer what came before the Big Bang. The question is whether the concept of before even makes sense. Because time, like space, may not be what we think it is. And if time itself began with the Big Bang, then asking what came before is like asking what is north of the North Pole. The question assumes a framework that does not apply, and that is where we go next. If the universe has structure, if it has laws, if it has a quantum vacuum humming with fields and zero-point energy, then somewhere underneath all that machinery sits time. Not time as a thing you can touch, not time as a river you can step into, but time as the framework that lets one moment follow another. The dimension that separates cause from effect, the axis along which entropy climbs and irreversible change unfolds. We talk about the Big Bang as the beginning of the universe, the moment 13.8 billion years ago when everything started. But that phrasing smuggles in an assumption. It assumes that time itself extends backward past the Big Bang, that there is a moment before which the universe did not exist and a moment after which it did. And that assumption, comfortable as it feels, might be completely wrong. Time does not work the way your intuition says it does. That's the first thing you need to accept before you can make any sense of what physicists mean when they say the Big Bang might be the beginning of time itself. In everyday life, time feels absolute. It flows forward at a steady rate. A second is a second whether you're sitting still or running, whether you are on Earth or on Mars, whether you are awake or asleep. Clocks tick at the same rate everywhere, or at least they appear to. Events have a clear order, cause precedes effect. The past is fixed. The future is open. That is the framework we use to navigate the world, and it works beautifully for everything you will ever do in your ordinary life. But it is not how time actually behaves when you look closely enough. Einstein's general theory of relativity, published in 1915, dismantled the idea of absolute time. Time is not a fixed background, an invisible clock ticking away uniformly across the cosmos. It is part of the structure of reality itself, woven together with space into a single four-dimensional entity called space-time. And space-time is not rigid. It bends, warps, flexes in response to mass and energy. Gravity in this picture is not a force pulling objects together. It is the curvature of space-time itself. A massive object like the Sun creates a dip in the fabric of space-time, and planets like Earth follow the curved paths around that dip, not because they are being pulled, but because they are moving along the straightest possible path through curved geometry. The key point for our purposes is that time is part of that fabric. It is not separate. It does not sit outside the universe watching events unfold. It is inside, embedded in the same structure that defines distance and location. And if space-time bends, then time itself can stretch, compress, and in some extreme cases stop making sense as a coordinate you can use to order events. The closer you get to a massive object, the slower your clock ticks relative to someone farther away. Spend a year orbiting near a black hole and you could return to find that decades have passed for everyone else. Time dilation is not science fiction. It is a measured, confirmed, thoroughly tested prediction of general relativity. Atomic clocks on airplanes tick at slightly different rates than atomic clocks on the ground. GPS satellites have to correct for time dilation, or their positioning data would drift by kilometers within hours. Time is flexible. Now take that flexibility and ask what happens at the Big Bang. According to general relativity, if you run the equations backward in time, winding the universe towards smaller and smaller scales, denser and denser states, you eventually reach a point where space-time itself ceases to be a smooth, well-defined structure. The curvature becomes infinite, density becomes infinite. The equations blow up, producing nonsensical results. Physicists call this a singularity, and it marks the boundary where the theory stops working. You cannot use general relativity to describe what happens at the singularity, because the theory itself is telling you it no longer applies. The rules break down. The singularity at the beginning of the universe is not a point in space. It is not a tiny dot sitting somewhere in an empty void, exploding outward. It is a boundary in time, a moment where the geometry of space-time becomes so extreme that the concept of time itself, as a coordinate you can use to label events, stops functioning. If you try to ask what happened 1 second before the singularity, the mathematics of general relativity says there is no such second. Not because something prevented it from existing, but because the coordinate system you're using to define before and after does not extend that far. Time, as a dimension, begins at the singularity. Asking what came before is like asking what is 1 kilometre north of the North Pole. The question assumes a direction that stops making sense at the boundary. That analogy, the North Pole analogy, shows up constantly in discussions of the Big Bang because it captures something essential about how physicists think about the origin of time. On the surface of the Earth, you can always go farther north, stand anywhere except the North Pole, and there is a direction you can travel that takes you closer to it. But once you reach the North Pole, the concept of north stops working. Every direction from that point is south. There is no farther north to go. The coordinate system, latitude, reaches its limit. You do not hit a wall, you do not fall off an edge, you just reach a point where the question of what is north of here has no answer, because the framework you are using to define north does not apply anymore. Time at the Big Bang works the same way. In the framework of general relativity, time is a coordinate, a label you assign to events so you can order them. As you move backward in time toward the Big Bang, the universe gets smaller, denser, hotter. Keep going and you approach the singularity. But the singularity is not an event that happened at some moment in time. It is the boundary of time itself. There is no moment before it in the same sense that there is no point north of the North Pole. The question of what came before the Big Bang is not a question physics can answer within the framework of general relativity, because the framework itself says there is no before. Time begins at the singularity. Full stop. This is not a cop-out. It is not physicists dodging a hard question. It is the natural conclusion you reach when you take general relativity seriously and apply it to the universe as a whole. Time is not an external stage on which the universe performs. It is part of the universe, part of the structure that gets created along with space and matter and energy. If the universe has a beginning, then time has a beginning. And if time has a beginning, then the word before stops meaning anything when applied to that boundary. Stephen Hawking spent much of his career thinking about this problem. He was not satisfied with simply declaring that the singularity marked the edge of physics and leaving it at that. He wanted to understand what, if anything, could be said about the earliest moments of the universe using the tools of quantum mechanics and general relativity together. In the early 1980s, Hawking and James Hartley, a physicist at the University of California, Santa Barbara, proposed an idea called the no-boundary proposal. It is one of the most elegant and one of the strangest attempts to describe the origin of the universe without invoking a moment of creation. The core idea is that the universe has no boundary in time, not because it extends infinitely far into the past, but because time itself behaves differently near the Big Bang. In the no-boundary proposal, as you move backward in time toward the singularity, time gradually transitions into something that looks more like space. The distinction between time and space, which is sharp in the universe we inhabit today, blurs and eventually disappears. The universe does not have a first moment. It does not have an edge where time begins. Instead, time smoothly curves into a spatial dimension, forming a closed surface with no boundary, no starting point, no initial condition that needs explaining. Hawking used the surface of the Earth as an analogy again, but this time in a different way. If you trace a line of longitude from the equator toward the North Pole, the lines of longitude get closer together as you approach the pole. At the equator, the the lines are far apart. At the pole, they all meet. But the surface of the Earth does not have an edge at the North Pole. It is perfectly smooth, perfectly finite, perfectly well-defined. There is no boundary, no singularity, no point where the geometry breaks down. The no-boundary proposal applies the same logic to the universe. Time, near the Big Bang, behaves like a line of longitude converging toward a point. But that point is not a singularity. It is just the smooth convergence of a finite closed geometry. The universe has a finite age, a finite extent in time, but no moment where time begins. The proposal is mathematically elegant, and it avoids the singularity problem by replacing the classical picture of the Big Bang with a quantum one. In this picture, the universe does not emerge from a singular point of infinite density. It emerges from a quantum state where the distinction between space and time is not yet fixed. The early universe, in this view, is not described by a single classical history but by a superposition of many possible geometries, all blending together in a quantum haze. The question of what came before the Big Bang does not arise because there is no sharp boundary to cross. Time fades into space, and the concept of before loses its meaning. Not everyone finds this satisfying. The no-boundary proposal is a theoretical idea, not a tested prediction. It makes assumptions about how quantum mechanics applies to space-time, assumptions that cannot yet be checked against observation. Some physicists embrace it as a profound insight into the nature of time and the origin of the universe. Others see it as a mathematical trick that sidesteps the hard questions without really answering them. The debate continues, and it will likely continue for decades, because we do not yet have the tools to probe the conditions near the Planck scale, where quantum gravity becomes important. What the no-boundary proposal does, whether it turns out to be correct or not, is force us to confront the limitations of our ordinary concepts when applied to extreme conditions. Time, as we experience it, is a robust, reliable, seemingly fundamental feature of reality, cause follows effect. Earlier moments influence later ones. The past is fixed, the future is open. But those features are properties of the universe in a particular regime, a regime where space-time is smooth, where quantum effects are negligible, where gravity is weak enough that general relativity and quantum mechanics can be treated separately. Near the Big Bang, none of those conditions hold. Space-time is not smooth. Quantum effects dominate. Gravity is strong enough to warp the fabric of reality into shapes we can barely describe mathematically, let alone visualize. In that regime, time might not flow. It might not have a direction. It might not even be a useful coordinate for labeling events. Asking what happened before the Big Bang is asking a question that assumes time extends past the boundary, where time itself is created. It is not that the answer is unknown. It is that the question is malformed. The framework you're using to ask it, a framework that assumes time is always there, extending infinitely in both directions, does not apply. Time is not always there. It is a feature of the universe, and like any feature, it has a domain where it makes sense and a boundary where it stops. The philosophical implications are unsettling. Causality, the idea that every effect has a cause, rests on the assumption that time is a well-defined sequence. Event A happens before event B, and if A influences B, then A is the cause and B is the effect. The chain of cause and effect can be traced backward, link by link, as far as you want to go. Philosophers and theologians have used this logic for centuries to argue for a first cause and uncaused cause, something or someone that set the chain in motion without itself needing a prior cause. If the universe had a beginning in time, the argument goes, then something outside the universe must have caused it. But if time itself begins with the universe, that argument collapses. Causality requires time. Without time, without a sequence of before and after, the concept of cause and effect does not work. You cannot ask what caused the Big Bang if the Big Bang is the moment when time begins, because the word caused assumes there was a moment before when the cause existed. If there is no before, there is no cause in the traditional sense. The universe does not need something to trigger it into existence, if existence is not an event that happens at a moment in time. It is the boundary, the starting point of the framework itself. This does not mean the universe popped into existence for no reason. It means the question of why it exists cannot be answered using the language of cause and effect. That language, powerful and intuitive as it is, applies within time. It does not apply to the origin of time. Some physicists take this as evidence that the universe is self-contained, that it needs no external cause because the framework of causality does not extend past the Big Bang. Others argue that the breakdown of our usual concepts near the singularity is a sign that we are missing something deeper, some more fundamental theory that would restore a sense of causality and explanation even at the boundary. The truth is, we do not know. General relativity says time begins at the Big Bang. Quantum mechanics says the singularity might not be a real feature of nature, but an artifact of using classical equations in a regime where they do not apply. Combining the two into a theory of quantum gravity, something physicists have been trying to do for nearly a century, might change the picture entirely. It might reveal that time does not begin at the Big Bang, but transitions smoothly from some earlier state. It might show that the universe is part of a larger structure, a multiverse or a cyclic cosmos, where the Big Bang is just one event in a longer history. Or it might confirm that time really does have a beginning, that the no-boundary proposal or something like it is correct, and that the origin of the universe is not a moment in time but the origin of time itself. Until we have that deeper theory, we are stuck with ambiguity. The equations we trust, the ones that describe the universe with extraordinary precision in every regime we can test, all point toward a singularity at the beginning, a moment where space-time breaks down, where our models stop working, where the concept of time itself becomes suspect. The singularity is not an observation, it is a prediction, an extrapolation, a place where the mathematics we use to describe reality runs into a wall. Whether the wall is real or whether it is a sign that we need better mathematics is the open question. NASA acknowledges this uncertainty in their public descriptions of the Big Bang. They describe the universe as undergoing rapid cosmic inflation around 13.8 billion years ago, and they note plainly that scientists are not sure what came before inflation or what powered it. That honesty is important. The Big Bang model is not a complete theory of the origin of everything. It is a description of how the universe evolved from a hot, dense state into the cosmos we observe today. The question of what, if anything, came before that hot, dense state is still open. Inflation might be part of a larger process. The Big Bang might not be the true beginning, but a transition from some earlier phase. Or it might be exactly what general relativity suggests, the origin of time, the boundary beyond which the question of before has no meaning. The Planck mission, which mapped the cosmic microwave background with unprecedented precision, refined the age of the universe to 13.787 billion years, give or take 20 million. That number is not the age of time itself in some absolute sense. It is the time that has elapsed since the hot Big Bang, measured using the ticking of light and the expansion of space. If time began at the Big Bang, then that number is the total age of time. If time existed in some form before the Big Bang, then 13.8 billion years is just the age of this phase of the universe, and the true age, if such a thing even makes sense, is older. We do not have the data to decide between those possibilities. We have a number, a measurement, a clock that we can wind backward to a specific point. What happens when that clock reaches zero, whether time stops or transitions or continues in some unfamiliar form, is beyond the reach of current observation. The philosophical implications ripple outward. If the universe has no definitive start in time, if the no-boundary proposal or something like it is correct, then the question of why the universe exists shifts. It is no longer a question about what happened at a moment of creation. It is a question about why the laws of physics are what they are, why space-time has the geometry it has, why the boundary conditions allow for a universe like ours to exist at all. Those are harder questions. They do not fit neatly into the framework of cause and effect. They are questions about the structure of reality, about the menu of possible universes, about the criteria that select one configuration over another. Some physicists think those questions have answers within physics, answers we might one day uncover through better theories and better observations. Others think they are the wrong questions, that asking why the laws are what they are is like asking why mathematics is consistent. The laws are what they are because that is the structure of reality, and structure does not need a cause. The North Pole analogy only takes you so far. It helps you understand why asking what came before the Big Bang might be a question without an answer. But it does not tell you what to do with that understanding. It does not tell you whether the boundary is fundamental or provisional, whether time really begins at the Big Bang, or whether that is just where our current equations break down. And it does not tell you what, if anything, lies beyond the boundary. Some physicists think the answer is nothing. Time begins, the universe begins, and that is the full story. Others think the boundary is a veil, hiding an earlier structure that we cannot yet describe. A pre-Big Bang universe, a collapsing phase that transitioned into expansion, a quantum foam giving birth to space-time, a multiverse where Big Bangs happen constantly in different regions. All of those ideas are speculative, but they are not random speculation. They are attempts to extend physics past the boundary where general relativity says the story ends. The truth is that time, at the deepest level, is mysterious. We use it every day, we measure it with extraordinary precision, we build our lives around it, and yet when you push it to its limits, when you ask what it is, where it comes from, whether it has a beginning, the answers dissolve into mathematics and philosophy and unresolved debates that have been running for decades. The Big Bang might be the origin of time, or it might be a transition, a phase change, a boundary in a larger structure where time behaves differently on the other side. We do not know. The evidence points toward a beginning, but the evidence is incomplete. The theories suggest a boundary, but the theories are provisional. What we do know is that asking what came before the Big Bang is not the same as asking what came before any other event. It is not like asking what happened before you were born or what happened before the Earth formed. Those questions assume time already exists, stretching backward without limit. The question of what came before the Big Bang asks about a moment when time itself might not have existed. And if time did not exist, then the word before has no referent. It points to nothing. The question collapses under its own weight. That does not mean the question is meaningless. It means the answer, if there is one, will require a deeper understanding of time, a more fundamental theory, a framework that can describe how time emerges, how it begins, how it connects to the other dimensions of space-time. Quantum gravity, whatever form it takes, will need to address this. String theory, loop quantum gravity, causal set theory, every candidate for a theory of quantum gravity has something to say about the origin of time and the structure of space-time at the Planck scale. None of them have been confirmed, none of them have made predictions we can test, but they are the tools physicists are building to answer the question you cannot help but ask. What came before? And those tools are starting to suggest answers. Not final answers, not confirmed answers, but answers that go beyond the North Pole analogy and start to describe what a pre-Big Bang universe might actually look like. The problem with asking what came before the Big Bang is not that the answer is hidden. It is that the question itself sits at the edge of what physics can handle. You have run the equations backward. You have watched the universe shrink down to a hot, dense state. You have seen time itself blur and bend near the boundary, where space-time stops behaving like a smooth fabric and starts looking more like quantum foam. And now you are standing at that boundary, staring into a region where the rules you trust, general relativity and quantum mechanics, both throw up their hands and say, "This is as far as we go." What lies beyond that boundary is not unknown, in the way that the far side of the moon was unknown before we sent a probe. It is unknown in a deeper sense. The boundary itself might be the end of the story, or it might be a transition, a phase change, a doorway into an earlier universe that operated under different rules. And if you want to know which one is true, you need to step outside the standard model of cosmology and start building what physicists call meta-theories. Frameworks that try to explain not just how the universe evolved after the Big Bang, but what the Big Bang itself emerged from. These are not wild guesses. They are not late-night dorm room philosophy dressed up in equations. They are serious attempts by serious physicists to extend the reach of testable science into a regime where testing becomes extraordinarily difficult. Some of these ideas are motivated by mathematics, by the internal logic of theories that work beautifully in other contexts and seem to demand a larger structure. Some are motivated by observations, by patterns in the data that hint at something deeper, and some are motivated by the sheer discomfort of accepting that the universe had a beginning without asking whether that beginning was itself the product of something earlier. The standard Big Bang model, combined with cosmic inflation, explains almost everything we observe. The temperature of the cosmic microwave background, the abundance of light elements, the large-scale structure of galaxies, the uniformity and flatness of space. It works. But it does not explain what powered inflation. It does not explain why the universe started in a state primed for inflation in the first place. It does not explain what, if anything, set the initial conditions. Those questions sit outside the framework, and answering them requires stepping beyond the Big Bang into territory that is far less certain. NASA is direct about this. They note that scientists are not sure what came before inflation, or what powered it. That uncertainty is not a flaw in the Big Bang model, it is a feature. The model describes what happened after a certain point. It does not claim to describe the origin of that point. And the gap between what we know and what we would like to know has become one of the most active areas of research in theoretical cosmology. The ideas that have emerged over the past few decades are strange, ambitious, and in some cases, impossible to test with current technology. But they are the best tools we have for thinking about the question that refuses to go away. What came before? The simplest extension of the Big Bang model, the one that feels the most natural if you are uncomfortable with the idea of an absolute beginning, is the cyclic universe. The concept is old, predating modern cosmology by thousands of years. Ancient Hindu and Buddhist cosmologies describe the universe as undergoing endless cycles of creation and destruction, each cycle spanning unimaginable spans of time. The idea fell out of favour in the West when the Big Bang model gained traction in the mid-20th century, but it never completely disappeared. In the 1930s, physicist Richard Tolman explored cyclic models mathematically, trying to see whether general relativity would allow a universe that expands, slows down, stops, and then collapses back on itself in a big crunch, only to bounce and begin expanding again. The math allowed it, but the models had problems. Each cycle increased the entropy of the universe, and there was no clear mechanism to reset the clock. The cycles could not be eternal. They had to start somewhere. Modern cyclic models are more sophisticated. They do not rely on a simple expansion and contraction driven by gravity alone. Instead, they incorporate ideas from quantum mechanics, string theory, and higher dimensional physics to provide a mechanism for the bounce. The universe, in these models, does not collapse into a singular point of infinite density. It contracts down to a very small, very dense state, and then quantum effects, the same effects that prevent electrons from spiraling into the nucleus of an atom, provide a repulsive force that halts the collapse and triggers a new expansion. This is called a big bounce, and it replaces the singular beginning of the Big Bang with a transition from a prior contracting phase. The idea is appealing because it sidesteps the singularity problem. If the universe bounces rather than collapsing to a point, then the equations do not blow up. There is no moment where density and curvature become infinite. The universe shrinks, but it never reaches zero volume. At the smallest scale, quantum mechanics takes over and prevents the collapse from continuing. The bounce is not an explosion. It is a rebound, like a ball hitting the ground and bouncing back up. The universe contracts, hits a minimum size set by quantum effects, and then begins expanding again. And if this can happen once, it can happen many times. The universe could be oscillating, cycling through expansions and contractions, with no beginning and no end. Just an eternal rhythm of growth and collapse and growth again. The most developed version of this idea is called the ekpyrotic model, named after the ancient Stoic idea of ekpyrosis, the periodic destruction and renewal of the world by fire. The ekpyrotic model, proposed in the early 2000s by physicists Paul Steinhardt, Neil Turok and others, combines cyclic cosmology with brain theory from string theory. In this picture, our universe is a three-dimensional brain, a kind of membrane, embedded in a higher dimensional space. There is another brain nearby, separated by a tiny gap in the extra dimensions. Every so often, the two brains collide. The energy of the collision heats both brains, filling them with radiation and matter, and the aftermath of the collision looks exactly like a Big Bang. Our Big Bang, in this view, was not the beginning of everything. It was the most recent collision between two brains that have been bouncing off each other for eternity. The model makes predictions. It predicts specific patterns in the cosmic microwave background, subtle differences in the distribution of temperature fluctuations that distinguish a cyclic bounce from a single inflationary event. So far, the observations have not confirmed those predictions. The data from the Planck satellite, the most precise map of the CMB we have, is consistent with standard inflation and does not show the signatures the ekpyrotic model predicted. That does not rule the model out completely. The signatures might be too small to detect with current instruments, but it does mean that cyclic cosmology, for all its elegance, is not supported by strong observational evidence. It remains a possibility, a framework that works mathematically and solves certain problems, but it is not the leading explanation. The bigger issue with cyclic models is the entropy problem. The second law of thermodynamics says that entropy, the measure of disorder in a system, always increases over time. In a cyclic universe, each bounce should leave the universe slightly more disordered than the previous cycle. Stars burn out, black holes evaporate, structures decay. If the universe has been bouncing for eternity, it should have reached maximum entropy long ago. The fact that we live in a universe with stars, galaxies, and complex structures suggests that the cycles, if they exist, cannot have been running forever. There must have been a first cycle, a beginning to the oscillations, and that brings you right back to the same question you were trying to avoid. What started the cycles? Why is there something rather than nothing? Cyclic models push the problem back, but they do not eliminate it. Another approach to the pre-Big Bang question comes from inflation itself. Standard inflation assumes that the inflationary phase ended everywhere at roughly the same time, transitioning into the hot Big Bang that produced the universe we observe. But some versions of inflation, collectively called eternal inflation, suggest that inflation never completely ends. It stops in some regions, creating bubble universes like ours, but it continues in others, stretching space and creating new regions where inflation will eventually stop and spawn more bubbles. The process is self-perpetuating. Once inflation starts, it never fully stops. It just keeps generating new universes, each one a pocket where inflation ended and a hot Big Bang began. In eternal inflation, our universe is not the universe. It is one bubble in an infinite sea of bubbles, each with its own Big Bang, its own laws of physics, its own history. The space between the bubbles is still inflating, growing faster than the bubbles themselves, so the bubbles never collide. They are causally disconnected, forever out of reach. You cannot send a signal from one bubble to another because the space between them is expanding faster than light. Each bubble is an isolated cosmos, and the inhabitants of each bubble, if there are any, would see their own CMB, their own horizon, their own observable universe, with no way to detect the others. Eternal inflation solves some problems. It explains why our universe seems fine-tuned for life. If there are infinitely many bubbles, each with different properties, then some of them will inevitably have the right conditions for stars, planets, chemistry, and biology. We live in one of those bubbles, not because the universe was designed for us, but because we could only exist in a bubble with the right properties. The vast majority of bubbles are lifeless, hostile, empty. We do not see those. We see the one that worked. This is called the anthropic principle, and it is one of the most controversial ideas in cosmology. Critics argue that it's not a real explanation, that it replaces the question of why our universe has the properties it does with a shrug, and a claim that it had to be this way because otherwise we would not be here to ask. Supporters argue that if eternal inflation is true, the anthropic principle is not a cop-out. It is a statistical fact. The challenge with eternal inflation is that it predicts a multiverse, and a multiverse is, by construction, largely unobservable. You cannot see other bubbles, you cannot measure their properties, you cannot test whether they exist. All you can do is look for indirect signatures, subtle patterns in the CMB or the distribution of galaxies that might hint at a collision between our bubble and another one in the distant past. So far, no such signatures have been found. Eternal inflation is mathematically consistent. It emerges naturally from many models of inflation, but it is not confirmed, and it may never be confirmable in the direct way that most scientific theories are. The multiverse idea comes in several flavors, and it is important not to conflate them. Eternal inflation gives you a multiverse of bubble universes, each one a separate space-time with its own Big Bang. String theory, the attempt to unify quantum mechanics and general relativity by describing particles as tiny vibrating strings, gives you a different kind of multiverse called the string landscape. In string theory, the laws of physics are not fixed. They depend on how the extra dimensions, the ones beyond the familiar 3 of space and 1 of time, are curled up and hidden. There are an enormous number of ways to curl up those dimensions, possibly 10 to the power of 500 different configurations, and each configuration gives you a different set of physical laws, different particle masses, different force strengths. If the universe explores all those configurations, then somewhere in the multiverse, every possible version of physics is realized. Our universe is just one point in that landscape, one configuration that happens to allow for atoms and chemistry and a life. Then there is the quantum multiverse, sometimes called the many worlds interpretation of quantum mechanics. In this picture, every time a quantum measurement occurs, every time a particle has a choice between multiple possible outcomes, the universe splits into branches, one for each outcome. The cat is both alive and dead, but in separate branches. You measure the spin of an electron and it is up in one branch and down in another. Both branches are real, both continue evolving, and the number of branches grows exponentially with every quantum event. This version of the multiverse has nothing to do with cosmic inflation or string theory. It is a consequence of taking the mathematics of quantum mechanics literally and refusing to add an extra rule that says only one outcome is real. Most physicists do not take the many worlds interpretation literally, but it is mathematically consistent and it solves certain conceptual problems with quantum mechanics, so it remains on the table. The problem with all these multiverse ideas is the same. They are hard to test. If other universes are causally disconnected from ours, if they exist in separate branches of the wave function, or in distant regions of an eternally inflating spacetime, then by definition we cannot observe them directly. The best you can hope for is indirect evidence. Maybe the parameters of our universe, the strength of gravity, the mass of the electron, the cosmological constant, show patterns that are easier to explain in a multiverse framework than in a single universe framework. Maybe there are anomalies in the CMB, cold spots or unexpected correlations that could be interpreted as scars from a collision with another bubble universe. Maybe the mathematics of string theory or quantum mechanics point so strongly toward a multiverse that rejecting it would be more ad hoc than accepting it. NASA does not take a firm position on the multiverse. They describe it as a theoretical idea that emerges from certain models, but they do not claim it is confirmed. The scientific community is split. Some physicists, like Max Tegmark and Brian Greene, embrace the multiverse as a natural consequence of our best theories. Others, like Paul Davies and George Ellis, argue that the multiverse is not science, because it makes no testable predictions. If a theory predicts that anything can happen somewhere in the multiverse, then it predicts nothing. It becomes unfalsifiable, immune to disproof, and that puts it outside the domain of empirical science. The debate is ongoing, and it touches on deep questions about what counts as a scientific explanation and what role observation should play in theory building. Brain cosmology, the idea that our universe is a brain in a higher dimensional space, offers another route to a pre-Big Bang scenario. In this picture, the Big Bang is not the origin of everything. It is a collision event, the moment when our brains smashed into another brain, releasing energy and creating the hot, dense state we call the early universe. The brains exist in a higher dimensional space called the bulk, and they can move through that space, approaching each other, colliding, bouncing apart, and potentially colliding again. Each collision generates a Big Bang, and if the brains oscillate, you get a cyclic cosmology, where the cycles are driven by brain collisions rather than gravitational collapse. The idea comes from string theory, which requires extra dimensions beyond the four we experience. In some versions of string theory, particles are confined to brains, three-dimensional surfaces embedded in a higher dimensional space. Gravity uniquely can leak off the brain into the bulk, which might explain why gravity is so much weaker than the other forces. If our universe is a brain, then what we call the Big Bang could be the result of a collision with another brain, and the energy of that collision would have filled our brain with radiation and matter, setting off the hot Big Bang phase. Brain cosmology makes some testable predictions, but they are subtle. The presence of extra dimensions might leave signatures in the gravitational waves produced during the collision, tiny deviations from what standard inflation predicts. The distribution of matter and energy at the moment of collision might differ slightly from what you get in a single universe model, and those differences could show up in the CMB. So far, the data does not clearly support brain cosmology. The Planck satellite data is consistent with standard inflation, and the signatures predicted by brain models have not been detected. That does not rule out the idea, but it means brain cosmology, like cyclic models and eternal inflation, remains speculative. It is motivated by theoretical considerations, by the mathematics of string theory, but it is not confirmed by observation. What all these ideas have in common is that they are attempts to avoid the conclusion that the Big Bang was an absolute beginning. They are uncomfortable with the singularity, uncomfortable with the idea that time itself started at a specific moment, uncomfortable with the notion that there was nothing before, and so they propose mechanisms, mathematical frameworks, extensions of known physics that allow for something before the Big Bang, a prior contracting phase, an eternally inflating multiverse, a collision of brains, a quantum bounce. Each one pushes the boundary back, replacing the singularity with a transition, replacing the origin of time with a longer history. But none of them eliminates the problem. Cyclic models still need a first cycle. Eternal inflation still needs an explanation for how inflation started in the first place. Brain cosmology still needs an explanation for why the brains exist and why they have the properties they do. The multiverse still needs an explanation for why the landscape has the structure it has. Every meta-theory pushes the question back a step, but the question remains: why is there something rather than nothing? Why these laws and not others? Why this structure and not a different one? The answers are not getting clearer. If anything, they're getting more abstract, more mathematical, more removed from the kind of direct observation that grounds the rest of science. Big Think, summarizing the state of the field, notes that what came before the Big Bang, and for how long, is still firmly in the realm of speculation. That is not a criticism. It is an acknowledgement of where the science stands. The standard Big Bang model with inflation is well supported by evidence. The extensions, the meta-theories, the pre-Big Bang models are not. They are frameworks for thinking about the origin question, tools for exploring what might be possible, but they are not settled science. They are not the kind of theories you find in textbooks next to general relativity and quantum mechanics. They are the cutting edge, the frontier, the place where physics meets its limits and starts reaching into territory that might not be reachable at all. That does not mean they are not worth pursuing. Science progresses by asking questions that seem impossible to answer, and then finding ways to answer them. Inflation itself was speculative when Alan Guth proposed it in the 1980s. The idea that the universe expanded faster than light, that quantum fluctuations got stretched to cosmic scales, that the CMB would carry the fingerprints of that process seemed almost too convenient. And then the observations came in, and inflation went from a speculative idea to the leading explanation for the structure of the early universe. The pre-Big Bang models might follow the same path, or they might not. The difference is that inflation made predictions that could be tested within a few decades. The multiverse, eternal inflation, cyclic cosmology, brain collisions, those ideas make predictions that are far harder to test. Some of them might be untestable in principle, forever beyond the reach of observation. And that brings you to the next uncomfortable question. If a theory cannot be tested, if it makes no predictions that distinguish it from alternatives, if it lives entirely in the realm of mathematics and philosophy, is it still science? The debate over that question is as fierce as any debate in cosmology. Some say yes. If the theory is motivated by established physics, if it solves real problems, if it makes the overall picture more coherent, then it counts as science even if it cannot be directly tested. Others say no. Science is about observation, about prediction, about confronting ideas with data. A theory that predicts everything predicts nothing, and a framework that cannot be falsified is not a scientific theory. It is metaphysics. The truth is probably somewhere in between. The pre-Big Bang models are not arbitrary. They are not made up out of thin air. They emerge from extensions of theories that work beautifully in other contexts. String theory explains particle physics and quantum gravity in ways that general relativity and quantum mechanics separately cannot. Eternal inflation is a natural consequence of the simplest models of inflation. Cyclic cosmology solves the singularity problem without invoking new physics. The ideas are grounded, but they are also speculative, and speculation, no matter how well motivated, is not the same as confirmation. What you're left with is a menu of possibilities. The universe might be cyclic, bouncing eternally between expansion and contraction. It might be one bubble in an eternally inflating multiverse. It might be a brain in a higher dimensional space, periodically colliding with other brains. It might have emerged from a quantum fluctuation in a pre-existing vacuum, or it might have had an absolute beginning, a moment when time itself started, and the question of what came before might be meaningless because there was no before. Each of these pictures is mathematically consistent. Each one solves certain problems, and each one remains, for now, beyond the reach of definitive proof. The evidence we have, the cosmic microwave background, the abundance of elements, the large-scale structure of galaxies, all points back to a hot Big Bang about 13.8 billion years ago. Everything before that is inference, extrapolation, and educated speculation. The data stops at the surface of last scattering. The theories go further, but the observations do not follow, not yet, and maybe not ever. That gap between what we can observe and what we can theorize is where the next chapter lives. The question is not just what came before the Big Bang, it is whether we can ever know, whether the tools of science, built to describe the observable universe, can reach back past the boundary where observation ends, whether there are questions that science, for all its power, cannot answer. Not because the answers are too hard, but because the questions themselves lie outside the domain where science applies. That is the edge of everything, and that is where we go next. The cosmic microwave background is a wall, not a physical barrier, not a curtain you could pull aside if you had the right equipment. A wall in the purest informational sense, a boundary beyond which electromagnetic signals cannot pass because the universe itself was opaque. Every telescope ever built, every detector ever pointed at the sky, runs into that wall at the same point, 380,000 years after the Big Bang, when atoms first formed and photons finally streamed freely through space. That is the earliest snapshot we have, and nothing we do with visible light, radio waves, X-rays, or any other form of electromagnetic radiation will ever get us past it. The CMB is not just the oldest light we can observe, it is the oldest light that exists to observe. Anything earlier is locked behind a fog so thick that light could not travel through it, and if light cannot reach us from that era, then every question we want to ask about what happened before, every theory we want to test about cyclic universes or brain collisions or quantum bounces, has to find some other way to gather evidence. The wall is not arbitrary. It is built into the structure of the early universe. Before recombination, the cosmos was a plasma. Free electrons zipped around, scattering photons in every direction. A photon could not travel more than a short distance before slamming into an electron and bouncing away. The universe was filled with light, but the light was trapped, pinballing endlessly through the plasma with no chance of escape. When atoms formed, the electrons got locked into orbits around nuclei and the photons were suddenly free. They have been travelling in straight lines ever since, cooling and stretching as space expanded. Until today they arrive at our detectors as faint microwaves, with a temperature just shy of 3 degrees above absolute zero. That light carries information about the universe at the moment it was released. The temperature, the density, the fluctuations that would eventually seed galaxies. But it carries no information about what happened before recombination, because there was no way for light to travel freely during that earlier era. The CMB is a photograph, but it is not a transparent window. It is the last surface light could scatter from before the universe became clear, and everything before that surface is hidden. NASA describes this plainly. The cosmic microwave background is the oldest light we can observe in the universe. That phrasing is precise. Observing the universe with light, with any form of electromagnetic radiation, has a hard limit, and that limit is the CMB. You cannot see past it. You cannot image the first 100,000 years. You cannot watch stars form before stars existed. You cannot peek into the inflationary epoch or catch a glimpse of the singularity. All of that is invisible to electromagnetic astronomy. And since electromagnetic astronomy is how we have studied the cosmos for the entire history of science, that poses a problem. A big one. If the tools that have carried us this far cannot reach any further, if the evidence we need to test pre-Big Bang theories is hidden behind a wall we cannot breach, then how do we make progress? How do we distinguish between competing ideas when the data we need is fundamentally out of reach? The answer, or at least the hope for an answer, lies in gravitational waves. Not the kind LIGO detects from colliding black holes or merging neutron stars. Those are late universe events, cosmic violence happening billions of years after the Big Bang. The gravitational waves physicists are hunting for in the context of the early universe are primordial. Ripples in space-time itself, generated during inflation or even earlier, travelling through the cosmos since the first moments after time began. Unlike light, gravitational waves do not interact with matter. They do not scatter off electrons. They do not get absorbed by plasma. They pass through everything, undisturbed, carrying information from eras when the universe was far too dense and far too hot for photons to move freely. If primordial gravitational waves exist, and if we can detect them, they would be the first direct observational tool we have ever had for probing the universe before the CMB. Gravitational waves are distortions in the fabric of space-time. When a massive object accelerates, it creates ripples that spread outward at the speed of light, stretching and squeezing space as they pass. The effect is tiny. LIGO, the most sensitive gravitational wave detector ever built, measures changes in distance smaller than the width of a proton over a stretch of several kilometers, detecting gravitational waves from colliding black holes, events that release more energy in a fraction of a second than the Sun will emit in its entire lifetime, required decades of engineering and the construction of instruments so precise they border on the absurd. Detecting primordial gravitational waves, faint echoes from the Big Bang itself, is orders of magnitude harder. The signal is weaker, the background noise is louder, and the frequencies are different, stretching across ranges that no single detector can cover. The most promising approach so far involves looking for a specific signature in the cosmic microwave background itself. Gravitational waves passing through space stretch and squeeze it in a particular pattern, and that stretching leaves an imprint on the light travelling through it. The CMB, uniform as it is, has tiny fluctuations in temperature and brightness. Those fluctuations have a structure, a pattern, that can be analysed statistically. Most of the fluctuations are what physicists call E-mode polarization, a pattern that looks like swirls and blobs, consistent with density variations in the early universe. But if primordial gravitational waves were present during inflation, they should have created a second type of pattern called B-mode polarization. B-modes look different. They have a twisting spiral structure that cannot be produced by density fluctuations alone. If you detect B-modes in the CMB, and you can rule out other sources like foreground dust in our own galaxy, then you have indirect evidence of gravitational waves from the earliest moments of the universe. In 2014, a team using the BICEP 2 telescope at the South Pole announced that they had detected B-modes. The news made headlines. Some reports described it as the first direct evidence of gravitational waves from the Big Bang. The discovery, if confirmed, would have been monumental. It would have provided the first observational window into the inflationary epoch, a direct look at the physics of the universe when it was less than a trillionth of a second old. The team was cautious in their initial announcement, noting that they had done their best to account for contamination from dust in the Milky Way, but they could not rule it out completely. Follow-up observations by the Planck satellite, which mapped the CMB across multiple frequencies with higher precision, showed that the signal BICEP 2 detected was consistent with dust. The B-modes were there, but they were not coming from primordial gravitational waves. They were coming from our own galaxy, from tiny grains of dust aligned by magnetic fields, glowing faintly in the microwave range and mimicking the signature the team was looking for. The result was not a failure. It was science working the way science is supposed to work. A claim was made, additional data was collected, and the claim was revised in light of that data. But it was a reminder of how hard this problem is. The signal the physicists are searching for is buried under layers of noise, dust in the Milky Way, radiation from the CMB itself, instrumental artifacts, cosmic rays. Every potential source of contamination has to be accounted for, modelled and subtracted, and even then the residual signal might be too faint to detect with current instruments. The search continues. New telescopes are being built, new detectors are coming online, and the sensitivity is improving year by year. But as of now, primordial gravitational waves remain undetected. The window they would open into the pre-CMB universe is still closed. Even if primordial gravitational waves are detected, even if the B-mode signal is confirmed beyond doubt, the information they carry is limited. Gravitational waves tell you that something happened, that space-time was disturbed, that energy was present in a particular form at a particular time. They do not tell you what caused the disturbance. They do not distinguish between different models of inflation. They do not prove that the universe bounced rather than beginning at a singularity. They are a data point, an observation, a piece of evidence that can constrain theories but not confirm them uniquely. Different pre-Big Bang models make different predictions for the strength and spectrum of primordial gravitational waves, and detecting those waves would narrow the list of viable candidates. But it would not give you a definitive answer. It would shift the debate, refine the parameters, push the frontier of knowledge a little further back. It would not solve the origin question. The challenge of testing pre-Big Bang theories goes deeper than the difficulty of detecting faint signals. The challenge is that many of these theories, by their nature, make predictions about regions of space-time that are causally disconnected from us. The multiverse, for instance. If eternal inflation is correct, if our universe is one bubble in an infinite sea of bubbles, then the other bubbles are beyond our horizon. Not beyond in the sense that they're too far away to see with current telescopes. Beyond in the sense that light from those regions will never reach us no matter how long we wait. The expansion of space is carrying them away faster than light can travel toward us. They exist, if they exist at all, in a part of the cosmos that is fundamentally unobservable. And if you cannot observe something, if there is no possible experiment that could detect it, then how do you test whether it is real? Some physicists argue that indirect evidence is enough. The theory of eternal inflation emerges naturally from the simplest models of inflation. If inflation happened, and the evidence strongly suggests it did, then eternal inflation is not an additional assumption. It is a consequence. You do not need to observe other bubble universes to justify believing in them if the theory that predicts them is already well supported by observations of our own universe. The logic is the same as inferring the existence of black holes before anyone directly imaged one. General relativity predicted black holes. Stars and galaxies behaved in ways consistent with black holes existing, and eventually we detected gravitational waves from black hole mergers and captured an image of the event horizon shadow around the supermassive black hole at the centre of the galaxy Messier 87. The black holes were real, and we knew they were real long before we had direct images, because the theory that predicted them was tested in other ways and passed every test. The counter-argument is that black holes, even before we imaged them, had observable effects. They bent light. They accelerated stars in their vicinity. They emitted X-rays when matter fell into them. The effects were detectable, measurable, testable. Other bubble universes, if they exist, have no observable effects on our universe. They do not bend light that reaches us. They do not gravitationally attract matter in our bubble. They leave no fingerprints in the CMB or the distribution of galaxies. The only reason to believe in them is that a theory which explains other things predicts they should exist. And if that is your standard of evidence, critics argue, then you have left the domain of empirical science. You are doing mathematics, not physics. You are building models that fit the data we have, but those models include components that can never be tested. And at that point, you're no longer engaged in the kind of science that has driven progress for the past few centuries. The debate is not settled, and it is not likely to be settled anytime soon. It touches on fundamental questions about what science is, what counts as evidence, and how much weight to give theoretical consistency when direct observation is impossible. Some of the most respected physicists in the world are on both sides of this divide. Max Tegmark, Brian Greene, Alan Guth all argue that the multiverse is a natural consequence of our best theories and should be taken seriously even if we cannot observe it directly. Paul Davies, George Ellis, and others argue that the multiverse hypothesis is untestable and therefore not scientific, no matter how elegant the mathematics behind it might be. The conflict is not about the data. Both sides agree on what we have observed. The conflict is about how to interpret theories that go beyond the data, how to handle predictions that cannot be checked, and whether physics should limit itself to claims that can be empirically verified, or whether it should follow the mathematics wherever it leads, even into regions we can never observe. What makes the situation more frustrating is that the tools we have, powerful as they are running up against fundamental limits. The Large Hadron Collider, the most energetic particle accelerator ever built, smashes protons together at energies high enough to recreate conditions similar to those in the first moments after the Big Bang. It discovered the Higgs boson. It confirmed the standard model of particle physics to extraordinary precision, and it has found nothing beyond the standard model. No supersymmetric particles, no extra dimensions, no hints of string theory. The absence of new physics at LHC energies is itself a puzzle, and it suggests that if new physics exists, it exists at energy scales far higher than anything we can currently probe. The Planck energy, the scale at which quantum gravity becomes important, is about 10 to the power of 19 giga-electronvolts. The LHC reaches energies of about 10 to the power of 4 giga-electronvolts. We are 15 orders of magnitude short. Building an accelerator powerful enough to probe Planck-scale physics would require a machine larger than the solar system, consuming more energy than the entire output of the sun. It is not happening, not in this century, probably not ever. Telescopes face similar limits. The James Webb Space Telescope can see galaxies forming a few 100 million years after the Big Bang. It cannot see earlier than that because there were no galaxies yet. Future observatories might push the boundary back a little further, detecting the first stars, mapping the dark ages, imaging the moment when the universe transitioned from neutral hydrogen to ionized plasma as the first stars lit up. But no telescope, no matter how powerful, will ever see past the CMB. The wall is not a technological limitation, it is a physical one. The universe before recombination was opaque. There is no light from that era to collect. You cannot build a better camera to see through fog that thick. You need a different tool, and the only tool on the horizon is gravitational waves. And as we have seen, detecting primordial gravitational waves is extraordinarily difficult, and even if they are detected, the information they carry is limited. The theoretical side is stuck as well. Quantum gravity, the framework that would describe space-time at the smallest scales and the highest energies, remains elusive. String theory is the leading candidate, but it has not made a single confirmed prediction in over 40 years of development. It requires extra dimensions that have never been observed, particles that have never been detected, and energy scales that cannot be reached with any conceivable experiment. Loop quantum gravity, the main alternative, suffers from similar problems. It is mathematically consistent, it avoids some of the issues string theory faces, but it makes no testable predictions either. Both approaches are attempts to unify general relativity and quantum mechanics, to build a theory that works at all scales and under all conditions. Both have been under development for decades, and neither has produced the kind of breakthrough that would allow physicists to definitively describe what happens at a singularity, whether singularities even exist, or what the universe looked like at the Planck time. The quest for a unified theory of everything, a single framework that explains all forces, all particles, all interactions, was once the holy grail of physics. Einstein spent the last decades of his life searching for it and failed. Hawking thought he might find it and came up short. The standard model of particle physics, combined with general relativity, explains almost everything we observe, but the two theories do not fit together. Quantum mechanics treats space-time as a fixed background. General relativity treats space-time as a dynamic field that bends and curves. You cannot merge them without something breaking. Every attempt to do so either produces infinities that cannot be removed, or requires assumptions about the structure of reality that cannot be tested. The hope was that a theory of everything would emerge from the unification, a set of equations so powerful and so complete that they would explain not just how the universe works, but why it works that way, why the constants have the values they do, why the forces have the strengths they have, why space has 3 dimensions instead of 5 or 12. That hope has not been realized. We do not have a theory of everything. We do not even have a clear path toward one. The lack of progress is not for lack of effort. Thousands of physicists have spent their careers working on these problems. Entire institutions are dedicated to quantum gravity, to string theory, to cosmology. The mathematical sophistication is staggering. The equations fill textbooks. The conferences are packed. And yet the experimental side, the side that actually tests the theories, has stalled. The energy scales are too high. The distances are too small. The signals are too faint. We are pushing the limits of what can be observed with current technology, and those limits are starting to look less like temporary obstacles and more like permanent boundaries. There might be questions that science, for all its power, cannot answer. Not because the answers are hidden, but because the tools we use to probe reality cannot reach the places where the answers live. Big Think, summarizing the state of the field, notes that what came before the Big Bang, and for how long, is still firmly in the realm of speculation. That is not a dismissal. It is an acknowledgement of where the evidence stops and the speculation begins. The Big Bang model is well tested. Inflation is strongly supported. The cosmic microwave background matches the predictions to ridiculous precision. The abundance of light elements formed during nucleosynthesis matches the calculations. The large-scale structure of galaxies, the distribution of matter, the expansion rate, all of it fits. The model works, but it works from the end of inflation forward. Everything before that is a blank. We have theories, we have equations, we have frameworks that extend the known physics into earlier eras, but we do not have observations, we do not have data, we do not have the smoking gun that would let us say with confidence that one picture is right and the others are wrong. NASA is equally direct about the uncertainty. They note that scientists are not sure what came before inflation or what powered it. That statement, simple as it is, captures the core problem. Inflation explains the uniformity of the CMB. It explains the flatness of space. It explains the origin of the density fluctuations that became galaxies. But it does not explain itself. What set up the conditions for inflation to begin? What caused the inflaton field, the hypothetical field that drove the exponential expansion, to exist in the first place? What determined its properties, its energy density, its potential? The answers to those questions lie outside the framework of standard cosmology. They require a deeper theory, a more complete picture, something that connects inflation to the quantum vacuum or to a pre-existing multiverse or to a cyclic bounce or to whatever came before. And right now we do not have that deeper theory. We have candidates. We do not have a winner. The frustration is palpable in the field. Cosmology has made extraordinary progress over the past century. We went from not knowing whether other galaxies existed to measuring the age of the universe to 3 significant figures. We mapped the cosmic microwave background. We detected gravitational waves. We imaged a black hole. The pace of discovery has been breathtaking. And now, just as we're closing in on the origin question, just as we're starting to ask what came before the Big Bang, we are running into walls. Observational walls, technological walls, theoretical walls. The questions are clear. The tools to answer them are not. And that gap between the questions we can ask and the answers we can reach is growing. Some of the predictions made by pre-Big Bang models are testable in principle. Cyclic cosmology predicts specific patterns in the CMB. Subtle differences in the distribution of temperature fluctuations that would distinguish a bounce from a single Big Bang. The ekpyrotic model, for instance, predicts a blue tilted spectrum of gravitational waves, whereas standard inflation predicts a red tilted spectrum. If primordial gravitational waves are ever detected with enough precision to measure their spectrum, that measurement could rule out one model or the other. Brain cosmology makes predictions about the behavior of gravity at short distances, deviations from the inverse square law that might show up in tabletop experiments or precision tests of general relativity. Eternal inflation predicts that our universe should have certain statistical properties, certain correlations in the CMB that reflect its status as one bubble among many. None of these predictions have been confirmed. Some have been ruled out by existing data. Others remain viable, waiting for better instruments or more precise measurements. The reality is that most of the pre-Big Bang ideas live in a grey zone. They are not confirmed. They are not ruled out. They are consistent with what we observe, but they do not make sharp, definitive predictions that would let us test them cleanly. They explain the same data that standard inflation explains, sometimes more elegantly, sometimes with fewer free parameters, but not in a way that gives you a clear experimental signature. And as long as that remains true, as long as the theories are consistent with the data but not uniquely favoured by it, the question of what came before the Big Bang will remain open, not because we're not smart enough to figure it out, not because the theories are wrong, but because the evidence we need to decide between them is hidden behind a wall we cannot see past, encoded in signals we cannot detect, or located in regions of space-time we cannot reach. The search for a theory of everything was supposed to solve this. The hope was that if we could unify quantum mechanics and general relativity, if we could write down a single set of equations that described all forces and all particles at all scales, then the origin of the universe would fall out as a natural consequence. The equations would tell us what the Big Bang was, where it came from, whether it was unique or one of many. The singularity problem would be resolved. The boundary conditions would be explained. The question of why there is something rather than nothing would have an answer grounded in physics, not philosophy. That hope has not been realized, and it is starting to look like it might not be realized in our lifetimes. The equations are too hard, the energy scales are too high, the experiments are too expensive, the theories are too speculative, and the gap between what we can calculate and what we can observe is not closing. If anything, it is widening. Quantum gravity is the key. Everyone agrees on that. General relativity works at large scales. Quantum mechanics works at small scales. But there is a regime, near the singularity, near the Planck time, where both are important and neither can be ignored. That is where the current theories break down, and that is where a theory of quantum gravity would take over. The problem is that building such a theory is extraordinarily difficult. Quantum mechanics and general relativity are based on fundamentally different principles. Quantum mechanics is probabilistic. General relativity is deterministic. Quantum mechanics treats time as absolute. General relativity treats time as part of a flexible space-time geometry. Merging the two requires rethinking some of the most basic assumptions in physics, and no one has figured out how to do it in a way that makes testable predictions. The lack of experimental guidance is crippling. In the past, when physics ran into theoretical dead ends, experiments provided the clues needed to move forward. The Michelson-Morley experiment ruled out the luminiferous ether and paved the way for relativity. The photoelectric effect forced physicists to take quantization seriously. The discovery of cosmic acceleration revealed dark energy. Every major breakthrough in physics has been driven by a combination of theory and observation, with each side informing the other. But in the case of quantum gravity, the observations are not there. We cannot probe the Planck scale. We cannot create conditions similar to the singularity. We cannot watch a universe begin. All we can do is theorize, calculate, and hope that someday, somehow, nature will give us a hint about which path to follow. That hint might come from gravitational waves. It might come from the CMB. It might come from a tabletop experiment that detects a violation of general relativity at short distances. It might come from a particle accelerator that finds something unexpected, some new particle or interaction that points toward a deeper structure. Or it might not come at all. The possibility that we are reaching the limits of what science can discover, that there are questions about the universe that will remain forever unanswered, because the evidence we need is fundamentally out of reach, is uncomfortable. It goes against the optimism that has driven physics for centuries, the belief that every question has an answer, and every mystery can be solved if you are clever enough and persistent enough. But it might be true, and if it is, then the question of what came before the Big Bang might be one of those questions. Not unanswerable because the answer does not exist, but unanswerable because the tools we have cannot reach it. The wall is real, and it might be permanent. Science has carried us further than anyone had a right to expect. From a species that spent most of its existence huddled around fires, terrified of the dark, inventing stories about gods and monsters to explain thunder and lightning, we have built telescopes that can see galaxies forming when the universe was barely out of infancy. We have written equations that describe the behavior of matter at temperatures higher than the core of any star. We have measured the age of everything, mapped the shape of space-time, detected ripples in the fabric of reality itself travelling across billions of light years. We have looked backward through time to within a fraction of a second after the Big Bang and reconstructed, with staggering precision, the history of a cosmos that no single human will ever see in its entirety. That is not a small achievement. That is not luck. That is the result of centuries of careful observation, rigorous thinking, mathematical discipline, and a stubborn refusal to accept easy answers when the hard ones were within reach. And yet, for all that progress, for all the confirmed predictions and Nobel Prizes and textbooks rewritten, we have arrived at a place where the tools that brought us this far cannot take us any further. Not because the tools are broken, not because we are not clever enough, but because the questions we are asking now sit at the edge of what those tools were designed to answer. The cosmic microwave background is a wall. Particle accelerators cannot reach the energies where quantum gravity becomes important. Gravitational wave detectors are still orders of magnitude away from the sensitivity needed to catch primordial signals from the earliest moments after the Big Bang. The mathematics of quantum mechanics and general relativity, powerful as they are, refuse to merge cleanly into a single framework that would let us describe what happens at a singularity. Every path forward runs into a barrier, and the barriers are not temporary. Some of them might be permanent. Some of the questions we are asking might not have answers we can reach through observation. And that is where science, whether it likes it or not, starts brushing up against philosophy. The question of what came before the Big Bang is not just a scientific question. It is a question about the nature of existence itself, about why there is something rather than nothing, about whether the universe needs a cause or whether it is self-contained and self-explanatory. Those are not the kinds of questions you settle with a telescope. You can gather data, you can constrain possibilities, you can rule out models that make predictions inconsistent with what you observe, but at some point the data runs out, and what you are left with is interpretation. Two physicists can look at the same cosmic microwave background, agree on every measurement down to the 8th decimal place, and still disagree about what it means. One might say the universe began at the Big Bang. That time itself started there, and asking what came before is a question without meaning. The other might say the Big Bang was a transition, that something existed before, and the fact that we cannot observe it does not mean it was not there. Both positions are consistent with the data. Neither can be ruled out by current observations, and so the debate shifts from what we can measure to what we think is more plausible, more elegant, more satisfying as an explanation. That is philosophy. Not bad philosophy, not unscientific philosophy, just philosophy. The kind of reasoning you do when the evidence runs out and you still have questions. Philosophers have been asking these questions for thousands of years, long before anyone had a telescope or knew what a galaxy was. Why is there something rather than nothing? Does the universe have a beginning, or has it always existed? If it had a beginning, what caused it? If it has always existed, why does it have the structure it does rather than some other structure? Ancient Greek philosophers debated whether the cosmos was eternal or created, whether it was finite or infinite, whether it had purpose or was the result of blind chance. They had no data, no experiments, no way to test their ideas. All they had was logic, and they used it to construct elaborate arguments about the nature of reality. Some of those arguments were brilliant, some were nonsense. None of them could be confirmed because there was no way to gather the evidence needed to decide between them. Modern cosmology changed that. For the first time in history, questions about the origin and structure of the universe became answerable through observation. Edwin Hubble measured the redshift of galaxies and discovered that the universe is expanding. Penzias and Wilson detected the cosmic microwave background and confirmed that the universe was once hot and dense. The Planck satellite mapped the temperature fluctuations in that background and measured the age of the universe to a precision of better than 1%. Cosmology stopped being a branch of philosophy and became a branch of physics. The questions were the same, but now they could be answered with data rather than speculation. That shift, from armchair reasoning to empirical science, was one of the great intellectual achievements of the 20th century. It was supposed to settle the old debates, to replace speculation with knowledge, to give us the answers the philosophers had been arguing about for millennia. It did, and it did not. The data answered some questions definitively. The universe had a hot, dense beginning about 13.8 billion years ago. It is expanding, and the expansion is accelerating. The cosmic microwave background is real, the Big Bang model is correct, and the steady-state theory is dead. Those debates are over, but the data also opened up new questions, deeper questions, questions that sit right at the boundary between physics and philosophy. What powered inflation? What set the initial conditions? What, if anything, came before the Big Bang? Why does the universe have the laws it does rather than different laws? Why is there a universe at all? The answers to those questions are not in the data, not yet, maybe not ever, and so cosmology, even as it has become more empirical, more rigorous, more grounded in observation, has not escaped philosophy. It has just moved the boundary. The questions we can answer with telescopes and equations have been answered. The questions that remain are harder, stranger, and less obviously solvable using the tools of science alone. Take the question of why the universe exists. That is not a question about how the universe works. It is a question about why there is a how in the first place. Physics can tell you how matter behaves, how forces interact, how space-time curves in response to energy. It can tell you that if you start with certain initial conditions and apply certain laws, you get a universe that looks like ours. But it cannot tell you why those laws exist, why those initial conditions held, or why there is a system of laws at all rather than no system. Those are not physics questions. They are metaphysical questions. They ask about the framework underneath the framework, the structure that supports the structure. And physics, by its nature, operates within a framework. It assumes there are laws. It assumes those laws are consistent. It assumes the universe behaves in ways that can be described mathematically. Those assumptions are not derived. They are not proven. They are the starting point, the foundation on which the entire edifice of science is built. And if you ask why the foundation is there, you have stepped outside the domain where science can give you an answer. That does not mean the question is meaningless. It means the answer, if there is one, will not come from an experiment. It will come from a different kind of reasoning, a kind that looks more like philosophy or theology than physics. Some scientists are comfortable with that, others are not. The discomfort is understandable. Science has been so successful precisely because it limits itself to questions that can be tested, to claims that can be checked against observation. The moment you start talking about things that cannot be observed, things that lie outside the universe or before time began or in other branches of the multiverse, you are no longer doing science in the traditional sense. You are building models, yes. You are using mathematics, yes. But you are not making predictions that can be falsified. And falsifiability, the idea that a claim is only scientific if there is some observation that could prove it wrong, has been the gold standard of science since Karl Popper laid it out in the middle of the 20th century. The multiverse is the clearest example of this tension. Eternal inflation predicts that our universe is one bubble in an infinite sea of bubbles, each one a separate cosmos with its own Big Bang, its own laws, its own history. The prediction follows naturally from the simplest models of inflation. If inflation happened, and the evidence strongly suggests it did, then eternal inflation is not an extra assumption. It is a consequence. The math leads there. The theory demands it. And yet the other bubbles, if they exist, are by definition unobservable. They are beyond our horizon, causally disconnected, forever out of reach. No telescope will ever see them. No experiment will ever detect them. No measurement will ever confirm that they are there. So is the multiverse a scientific hypothesis or a philosophical speculation? Is it a prediction of physics or an untestable consequence of a theory that works for other reasons? The debate over that question is fierce, and it cuts to the heart of what science is. George Ellis, a cosmologist and philosopher of science, has argued that the multiverse hypothesis is not scientific because it makes no testable predictions. If anything can happen somewhere in the multiverse, then the theory predicts nothing. It becomes a framework where any observation, no matter how strange, can be explained by saying it happened in this particular bubble. That is not science. That is storytelling. Max Tegmark, on the other hand, argues that the multiverse is no different from any other part of physics that deals with unobservable entities. Quarks were unobservable when they were first proposed. Black hole interiors are unobservable by definition. The far side of the cosmic horizon is unobservable. We accept those things as real because the theories that predict them make other predictions that can be tested, and those predictions turn out to be correct. The multiverse, in this view, is just one more unobservable consequence of a theory that is well supported by the things we can observe. Both arguments are reasonable, both are internally consistent, and neither can be settled by pointing a telescope at the sky. The question of whether the multiverse is real is not a question about what exists. It is a question about what counts as a valid inference from the data we have. It is a question about the rules of evidence, about how much weight to give mathematical consistency when direct observation is impossible. And those are not scientific questions. They are questions about the philosophy of science, about the criteria we use to decide what claims are justified and what claims are not. Science cannot answer those questions because science operates within a set of rules, and the debate is about what those rules should be. The same tension shows up in the debate over fine-tuning. The universe, it turns out, is exquisitely sensitive to the values of its fundamental constants. The strength of gravity, the mass of the electron, the cosmological constant, dozens of parameters that determine how matter behaves and how forces interact. All of them have to fall within narrow ranges for stars to form, for chemistry to happen, for life to be possible. Change any one of those parameters by a small amount and you get a universe that is sterile. No stars, no planets, no atoms heavier than hydrogen, just a cold, empty void or a short-lived fireball that collapses back on itself before anything interesting can happen. The odds of all those parameters landing in the narrow range that allows for complexity seem vanishingly small, and yet, here we are. There are two ways to interpret that. One is to say the universe was designed, that the parameters were chosen by some external intelligence to allow for life. That is the theological answer, and it has a long history. William Paley made the argument in the early 19th century using the analogy of a watch. If you found a watch lying on the ground, you would not assume it formed by accident. You would infer that someone designed it, that its parts were arranged intentionally to serve a purpose. The universe, Paley argued, is far more complex than any watch, and so it too must have a designer. The fine-tuning argument is a modern version of the same logic. The parameters are too finely balanced to be the result of chance, therefore something or someone set them. The other interpretation is the multiverse answer. If there are infinitely many universes, each with different values for the fundamental constants, then some of them will inevitably have the right values for life. We live in one of those universes not because it was designed for us, but because we could only exist in a universe with the right conditions. The vast majority of universes are lifeless, and no one is there to notice. This is the anthropic principle, and it replaces design with statistics. You do not need a designer if you have a large enough sample space. Roll the dice enough times and you will eventually get the result you are looking for. Both answers are logically consistent, both explain the fine-tuning, and neither can be tested. You cannot observe the designer if there is one. You cannot observe the other universes if they exist. The choice between the two comes down to which explanation you find more plausible, more parsimonious, more consistent with everything else you believe about how reality works. And that is not a scientific choice, it is a philosophical one. Science gives you the data, the universe is fine-tuned, the parameters fall within narrow ranges, that much is confirmed. What you do with that data, how you interpret it, whether you see it as evidence for design or evidence for a multiverse or just a brute fact that needs no further explanation, that is up to you. The data does not decide. The observations do not tell you which interpretation is correct. You have to make a judgment call, and judgment calls are philosophy. Stephen Hawking understood this better than most. He spent his entire career working at the intersection of physics and philosophy, asking questions that could not be answered with experiments alone. In his final book, Brief Answers to the Big Questions, he tackled the question of whether the universe needs a creator. His answer was no, and his reasoning was rooted in physics. If time began with the Big Bang, if there is no moment before the singularity, then there is no time when a creator could have acted. Causality requires time. Without time, without a sequence of before and after, the concept of a cause breaks down. The universe does not need a creator because the framework that would allow for creation does not extend past the boundary where time begins. That argument is elegant and it follows directly from general relativity, but it is not a proof. It is an interpretation. It assumes that time really does begin at the Big Bang, that the singularity is not an artifact of incomplete physics, that there is no deeper structure underneath space-time where the concept of before still applies. Those are reasonable assumptions, but they are assumptions. Other physicists, equally brilliant, equally rigorous, make different assumptions and reach different conclusions. Roger Penrose, a Nobel Prize-winning physicist who worked closely with Hawking on singularity theorems, has proposed a cyclic cosmology where the Big Bang is not the beginning, but a transition from a prior contracting phase. In his model, called conformal cyclic cosmology, the universe goes through an infinite series of cycles, each one beginning with a Big Bang and ending in a cold, empty state, where all matter has decayed and only radiation remains. At that point, the distinction between a very old, very large universe and a very young, very small universe disappears, and the ending of one cycle becomes the beginning of the next. Time does not begin. It cycles. The Big Bang is not the origin of everything. It is just the most recent reset. Penrose's model is mathematically consistent. It solves the singularity problem. It makes some predictions about patterns in the cosmic microwave background that could, in principle, be tested. But it is speculative, built on assumptions about the far future of the universe that cannot be checked for trillions of years. And it replaces one mystery with another. If the universe cycles eternally, why does it cycle? What determines the structure of each cycle? Why does the process happen at all? The questions do not go away, they just move. The philosopher Bertrand Russell once said that the universe is just there, and that is all. He was responding to the argument that everything must have a cause, that the chain of causality must trace back to a first cause, an uncaused cause that set everything in motion. Russell rejected that logic. Why, he asked, does the universe need a cause? Why can the chain not simply end with the universe itself? If you are willing to accept that God does not need a cause, that God is self-existent and eternal, then why not apply the same reasoning to the universe? Why add an extra layer? Why not stop at the universe and say it is self-existent and eternal, or at least self-existent and temporal, and leave it at that? The argument is simple, direct, and impossible to refute using logic alone. It is also impossible to prove. The question of whether the universe is self-explanatory, or whether it requires an external explanation, is not a question science can answer. It is a question about the structure of explanation itself, about what counts as a satisfying stopping point, about where you're allowed to end the chain of why. NASA, in its public-facing descriptions of cosmology, is careful not to wade into these debates. They describe the Big Bang as the moment the universe began expanding from an extremely hot, dense state. They note that scientists do not know what came before inflation or what powered it. They acknowledge that much remains unknown. The phrasing is neutral, precise, and appropriately humble. It reflects the state of the science, which is that we have a model that works extraordinarily well from the end of inflation forward, and we have speculation, some of it well motivated and some of it not, about what might have come before. The speculation is not random. It is grounded in extensions of known physics, in theories that solve other problems, in frameworks that unify disparate phenomena. But it is still speculation, and NASA, as a scientific institution, is not in the business of endorsing speculation when the data is not there to back it up. The data might come. Primordial gravitational waves, if they are ever detected, would open a window into the earliest moments after the Big Bang, giving us information about the energy scales and the dynamics of inflation that we do not currently have. Advances in quantum gravity, if they happen, might give us a framework for describing what happens at a singularity, whether singularities are real or whether they are artifacts of using classical equations in a regime where quantum effects dominate. Future telescopes might find patterns in the cosmic microwave background that distinguish between competing models of the early universe, ruling some out and strengthening others. The search continues. The instruments get better. The theories get more refined, and every so often someone finds a piece of evidence that shifts the landscape, that rules out an old idea or breathes life into a new one. That is how science works. Slowly, incrementally, building knowledge one observation at a time. But the biggest questions, the ones about why the universe exists and what came before the Big Bang, and whether time had a beginning, those questions might not yield to that process. They might be questions that sit at the edge of what science can do, where the tools we have cannot reach the answers we want. And if that is the case, then the answers, if they exist at all, will come from a different kind of inquiry. Not from experiments or telescopes, but from reasoning about the nature of existence, the structure of causality, the relationship between mathematics and reality. That is philosophy. Not physics dressed up as philosophy. Not bad science trying to sound deep. Just philosophy. The kind of thinking humans have been doing for as long as they have had language, trying to make sense of where they came from and why anything is here at all. The relationship between science and philosophy is not adversarial. It never has been. The best scientists have always been philosophers, whether they admitted it or not. Newton wrote as much about theology as he did about mechanics. Einstein worried about whether God had a choice in creating the universe. Hawking spent decades thinking about the meaning of time and the nature of existence. The questions that drive science are philosophical questions. Why does the universe follow laws? Why are those laws mathematical? Why is there order rather than chaos? Science answers the how. Philosophy asks the why. And when you push science far enough, when you follow the chain of explanation all the way back to the origin of everything, the how and the why start to blur. You cannot separate them cleanly. You cannot do cosmology without eventually confronting the question of why the universe is the way it is, and that question does not have a scientific answer. It has interpretations, frameworks, models, some more compelling than others, but it does not have an answer in the way that the age of the universe has an answer, or the temperature of the cosmic microwave background has an answer. The philosopher Thomas Nagel wrote that the existence of anything at all is the most fundamental mystery. Not the existence of this particular universe with these particular laws, just existence. The fact that there is something rather than nothing. Science can explain how one thing leads to another, how matter behaves, how forces interact, how structures form. It cannot explain why there is a system of matter and forces and structures in the first place. That question sits outside the reach of empirical inquiry because there is no experiment you can do, no observation you can make, that would answer it. You can trace causes backward, but the chain has to start somewhere, and whatever you point to as the starting point, the question remains. Why that? Why not nothing? The question is not unanswerable because we lack data. It is unanswerable because the kind of answer it demands, an explanation for existence itself, is not the kind of thing science is built to provide, and yet the question refuses to go away. Humans have been asking it for as long as there have been humans, Every culture, every civilization, every era has produced its own answers, its own stories about where everything came from and why it is here. The stories are different, but the impulse is the same. We want to know. We want the universe to make sense. We want there to be a reason, a purpose, a structure underneath the chaos. Science has given us more answers than any other method humans have ever tried. It has explained the stars, the planets, the origin of elements, the age of the Earth, the evolution of life, the expansion of the cosmos. It has taken questions that were once the domain of myth and religion and turned them into questions we can answer with telescopes and equations. That is an extraordinary achievement. But it has not answered the biggest question, and it might never answer it. Not because science is failing, but because the question might sit outside the domain where science applies. The wonder is not that we have limits. The wonder is that we have come this far, that a species of primates, descendants of fish that crawled out of the ocean, built machines that can see light from when the universe was less than 400,000 years old, that we can measure the curvature of space-time, detect gravitational waves from black holes colliding billions of light years away, map the distribution of galaxies across the observable universe, that we can write equations that describe the first trillionth of a second after the Big Bang, and have those equations match the data. That is not a small thing. That is not luck. That is the result of curiosity, discipline, and a refusal to accept ignorance when knowledge was within reach. We stand at the edge of everything, looking back at a history that stretches 13.8 billion years into the past, forward into a future that will last trillions of years more, and outward across a cosmos so vast that light from its farthest reaches will never reach us. We have mapped the cosmos, measured it, understood it in ways that would have seemed like magic to anyone living even a century ago. And yet the deepest questions remain, not because we have failed, but because we have succeeded well enough to reach the boundary where science and philosophy meet, where the tools that brought us this far cannot take us any further, where the answers we seek might require a different kind of inquiry. The search continues. It always will, but the search itself, the act of asking why and how and what came before, is as close as we may ever come to understanding our place in a universe that, for all its vastness and all its mystery, allowed us to exist long enough to wonder. We asked what came before the Big Bang. The honest answer is that we do not know. The slightly longer answer is that the question itself might not mean what we think it means. If time began with the universe, if the singularity is not a moment in time but the boundary of time, then before stops being a direction you can point toward. The framework that lets you ask what happened earlier does not extend past the point where earlier is defined. That is not a dodge. That is what the mathematics of general relativity actually says when you take it seriously and follow it all the way back. But the mathematics might be lying, not in the sense that it is wrong, but in the sense that it is incomplete. General relativity breaks down at the singularity. Quantum mechanics does not play nicely with curved space-time. The tools we trust, the equations that describe everything we have ever observed, both throw up their hands at exactly the moment we need them most, and so we build extensions, cyclic cosmologies, eternal inflation, quantum bounces, brain collisions, multiverse frameworks where our Big Bang is just one event in a larger structure that has no beginning and no end. Every idea pushes the boundary back. None of them eliminates the question. They just rephrase it. What we are left with is not ignorance. It is the edge of what observation can reach and theory can describe. We have traced the history of everything back to within a fraction of a second after it all began. We have measured the temperature of creation itself, still glowing faintly in the sky above us. We have confirmed that the universe had a beginning, that it was once unimaginably small and hot, and that it has been expanding and cooling ever since. That is not speculation. That is fact, tested and retested, confirmed by every instrument we have pointed at the cosmos. The question of what came before that beginning, if anything, sits at the boundary where science ends and something else begins. Not religion necessarily, not mysticism, just a different kind of question, one that asks not how things work but why there are things at all. Science brought us to the edge. It cannot take us past it. Not yet, maybe not ever. And standing at that edge, looking back at everything we have learned and forward into everything we cannot see, the most honest thing we can say is this: the universe is here. We are here. And the fact that we can ask the question That we can look 13.8 billion years into the past and wonder what came before is itself one of the strangest and most unlikely things the cosmos has ever produced, as new signals arrive from the oldest light and deepest gravity, keep asking not only what the universe reveals, but what our questions quietly assume.